Hello there and welcome back to the Sleep Science. Tonight you drift weightlessly through the silent dark surrounded by a gauzy ocean of starlit mist. Wisps of hydrogen and helium swirl past your fingertips, faintly glowing, where ultraviolet light brushes them. You could almost imagine this as fog over a sleeping valley, except this fog stretches for dozens of light years, a cradle vast enough to hold 1,000 suns. It's peaceful, too peaceful. And you probably won't survive this, because if you were really here, your lungs would implode and your atoms would scatter into the vacuum faster than you could blink. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And I'd love to know, where are you watching from, and what time is it there? Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The scene around you begins to change. The gas cloud, this enormous nebula, is no longer as still as it first seemed. Within its depths, gravity whispers to every grain of dust and every stray atom, coaxing them together. You drift closer to one small knot of matter, barely denser than the rest, yet destined for greatness. Over millions of years, so long that human history would fit in a single blink, the cloud collapses. The denser it grows, the faster it pulls in the rest, like a lazy snowball suddenly remembering it can become an avalanche. You can feel it, the temperature rising from mere tens of degrees above absolute zero to thousands. Tiny shocks spark between clumps of gas, and deep inside, the first murmurs of fusion threaten to ignite. Stars, as it turns out, are the most patient pyromaniacs in the universe. They wait billions of years, gathering fuel, building pressure, until one day gravity squeezes just a little too hard and poof, the universe lights another candle. If you pause here and glance around, you'll see the same process happening everywhere. Some regions glow pink and blue, the colours of ionized hydrogen, while others remain dark, silhouetted against brighter dust. The Eagle Nebula, for instance, the one NASA captured in that famous Pillars of Creation photo, holds dozens of embryonic stars just like this, still tucked inside their dusty cocoons. Historians still argue whether that photo changed public interest in space more than the moon landing did, but it certainly made the cosmos feel a little more like home decor. Drifting deeper, you notice the first spark. Hydrogen atoms colliding under immense pressure fuse into helium, releasing a burst of light so intense that even the surrounding gas begins to glow. A protostar is born. It's still shy, not yet stable enough to shine steadily, flickering as it gulps down more material. Every second, gravity wins a small victory against emptiness, forcing matter into tighter intimacy. You can almost hear the sigh of the universe saying, "Finally!" There's something poetic about how stars form, not as explosions, but as slow compromises between chaos and order. The ancient Babylonians looked up and saw these lights as the eternal eyes of gods, watching from beyond the sky's curtain. Millennia later, modern astronomers realized those same points of light were vast spheres of plasma, each one a nuclear forge. And even though the myth was wrong, the feeling wasn't. The stars do watch, in a way. Their light tells us what they're made of, how hot they burn, even how fast they're moving. As you float around this growing star, waves of radiation buffet your invisible body. Dust particles cling together into pebbles, pebbles into rocks, and eventually into the kind of debris fields that will one day become planets. A single grain of silicon here might end up inside a world where oceans ripple under alien moons. It's humbling, really, how little the universe wastes. You watch as the protostar's outer shell begins to spin faster, flattening into a disk. If you look at it from above, it resembles a glittering vinyl record made of gas and dust, each groove humming a slightly different temperature. Somewhere in that disk, turbulence creates tiny vortices, cosmic whirlpools that trap more material, spiraling inward toward the center. Within a few million years, the central mass will ignite fully, its core hot enough to sustain hydrogen fusion continuously. The flickering candle will become a true sun. There's a quirky tidbit tucked in this phase of stellar evolution. Before a protostar stabilizes, it often experiences violent mood swings. Astronomers call these T-Tauri outbursts, sudden flares when the star belches jets of plasma out its poles. Imagine a newborn trying to sneeze out the afterbirth of its own creation. Those jets can stretch for light years, carving glowing tunnels through the surrounding nebula. The Orion Nebula, for instance, is full of these streaks, cosmic baby photos caught mid-sneeze. You float through one of those jets, feeling the charged particles stream past, painting neon streaks in the darkness. For a moment, it looks almost festive, like the universe is throwing its own confetti, and maybe it is. Every star that forms is another opportunity for life, chemistry, and stories. Without these collapses, there would be no elements heavier than hydrogen and helium, no carbon for your cells, no oxygen for your breath, no iron for your blood. Every heartbeat you've ever felt began quite literally in a collapsing cloud like this one. Eventually the chaos settles. The gas thins, the light steadies, and the newborn star begins to shine with confidence. Around it, the leftover debris cools into planets, comets, and asteroids, the raw ingredients for whatever stories might unfold there. You linger a little longer, watching the faint pulse of the star's light ripple through space, a silent announcement that a new source of warmth has entered the cosmic stage. Billions of years from now, this light will wash across empty space and perhaps be captured by some far-flung observer wondering how stars are born. They'll call it by some catalogue name, HD something something. But the universe will remember the moment you're witnessing now, the first breath of a star. You drift back slowly, the nebula now glowing like the inside of a softly lit lantern. The once chaotic cloud is peaceful again, but not the same kind of peace as before. It's a peace that hums with potential energy, like the silence right after a song ends but before applause begins. Somewhere deep inside, you feel the warmth of that starlight and realize it's the same warmth that eventually made you. You're still drifting in that soft afterglow, watching the newborn star pulse like a slow heartbeat when you feel it, the deep, invisible squeeze of gravity continuing its endless work. The cloud around the star keeps collapsing, but now the focus shifts inward, where pressure mounts in the core like an unspoken promise. Gravity, that patient sculptor, doesn't rush. It just keeps gathering, compressing, and whispering to the atoms, closer. Each time they obey, the temperature rises. By the time you reach the center of this stellar embryo, the heat is tens of millions of degrees. The air, if you could call it that, isn't air at all. Its plasma is so dense that a teaspoon of it would outweigh a mountain. And yet, in all that chaos, there's balance, an eerie equilibrium between collapse and expansion. You float near the center, where the pressure is indescribable. Here, hydrogen atoms are squished so tightly together that their protons begin to ignore the electric repulsion that normally keeps them apart. It's like watching two people who can't stand each other suddenly decide to hug for the sake of survival. When they merge, they form helium, and in that moment, a tiny spark of light is born. Multiply that by roughly a septillion per second, and you get a star's heartbeat. The young star's surface begins to stabilize, its turbulent mood swings calming into rhythm. You can almost hear it humming, a deep bass vibration that resonates through space itself. Astronomers have actually recorded something like this. They call it helioseismology. By studying the oscillations in a star's brightness, they can hear the sound waves bouncing inside it. The sun, for example, thrums like an enormous subwoofer, though its rhythm is far too slow for human ears to catch. Historians still argue whether the ancient Egyptians, with their sun hymns and gold-laden tombs, somehow sensed that the sun truly sings, or whether that's just poetic coincidence. As the core compresses further, gravity becomes almost meditative in its persistence. You can imagine it as a sculptor shaping clay, except the clay keeps trying to explode. For every squeeze, the star pushes back with heat and light. The moment it finds balance, when the outward pressure from fusion equals the inward pull of gravity, a star officially switches on. From the outside, it looks instantaneous. But inside, it's the culmination of millions of years of microscopic negotiations between physics and fate. You move outward from the core now through layers of plasma so dense and hot that light itself takes thousands of years to escape. Yes, really. A single photon born in the center of a star might bounce, scatter, and ricochet for millennia before finally reaching the surface. If you think your morning commute is bad, imagine being a particle of light stuck in cosmic traffic for 10,000 years, only to exit and sprint across space at light speed for the rest of eternity. That trapped radiation heats the outer layers, making them churn like a pot of boiling water. You can see massive convective currents rising and falling, each plume bigger than Earth itself. It's mesmerizing, swirls of plasma that twist and tumble. glowing with a colour that no paint could capture. Occasionally, magnetic fields twist those flows into loops that burst from the surface, forming sunspots and solar flares. They are beautiful, yes, but they're also reminders of how volatile this equilibrium really is. There's a curious fact astronomers like to share. Gravity isn't really a force pulling things together in the classic sense. It's more like space-time curving under mass, and everything simply following the curve. So when you feel gravity's squeeze here, it's not that the star is being hugged by some invisible hand, it's more space itself folding inward. Kind of a weird cosmic origami lesson. Einstein's general relativity made that clear, and ever since, physicists have looked at stars not just as fireballs, but as sculpted dents in reality. If you could zoom out now, you'd see hundreds of these gravitational wells dotting the nebula, each one gathering its own material. Some of those will become red dwarfs, small, cool and long-lived. Others, like this one, will grow massive and burn fiercely, destined for a much more dramatic end. You can already sense its potential. The deeper the gravitational collapse, the hotter the core and the more ferocious the future. But there's something humbling about this process too. Gravity doesn't discriminate. It builds stars, but it also tears them apart. The same force that brings life to the universe will one day extinguish it. It's the ultimate cosmic paradox. Creation and destruction, both sculpted by the same invisible curve. You can't help but feel that familiar tingle in your chest, an odd mix of awe and melancholy. You float higher, near the boundary between the inner radiative zone and the outer convective zone. The heat is less intense here, but the energy transfer is wild. Geysers of plasma surge upward, releasing energy that will eventually emerge as starlight. Imagine billions of tiny explosions, all synchronized, all driven by that same gravitational squeeze. It's chaos, yet there's an order to it. You start to realize that stars are not just massive balls of gas. They're living systems, each with a pulse, a metabolism, even moods. Here's a quirky side note. In the 9th century, before nuclear fusion was understood, scientists believed the sun shone because of gravitational contraction alone. Basically, it was slowly shrinking and heating up. According to their math, that could have powered the sun for about 20 million years, which of course didn't quite fit with the fossil record on Earth suggesting life had been thriving for hundreds of millions. Historians still argue whether Lord Kelvin's stubborn insistence on that theory slowed the progress of astrophysics, or just gave future scientists a good cautionary tale about scientific humility. Either way, it's a reminder. Even the smartest among us can underestimate how generous stars really are. As you watch, the star's light intensifies, reaching a steady golden brightness. The surrounding nebula glows in reflection, an illuminated halo marking the site of the birth. The leftover gas and dust begin to thin out, nudged away by solar winds, and it's, if they form here, will have to do so quickly before the light sweeps away the raw materials. You can almost hear a sigh, a sort of cosmic exhale. The labour is over. The baby is breathing, and as you drift in that soft radiance, you realise that gravity, the squeeze that started all this, never truly lets go. Even now it holds every atom in place, every orbit in check, every heartbeat steady. It's not just the reason stars shine, it's the quiet rhythm of the universe itself. You take one last look at the luminous sphere before you, glowing steady against the velvet dark. The light feels almost familiar now, the way sunlight does through your eyelids on a summer morning. It's hard not to smile. After all, this very process, repeated across billions of stars, is why you exist to witness it at all. You drift closer to the star's blazing surface, where gravity and heat perform a ceaseless duet. The glow that once felt gentle now blazes with such intensity that the darkness behind you fades to nothing. Here, in the hydrogen-burning core, fusion is no longer a whisper. It's a roar you can feel through the fabric of space itself. Each second, hundreds of millions of tons of hydrogen are consumed, and yet the star hardly notices. It's like watching a bonfire that feeds on itself, effortlessly balancing destruction with creation. You don't just see the process, you feel it in your bones, as if your own atoms remember where they came from. Inside, hydrogen nuclei, just single protons slam together at impossible speeds. Normally, they repel each other because positive charges aren't fond of sharing space, but down here the temperature is around 15 million degrees, and that changes the rules. Protons get so close that the strong nuclear force, the universe's most intimate handshake, snaps them into a single nucleus. 1 fusion, 2 fusion, 3, and soon helium appears. This is the proton-proton chain, the fundamental engine of stars like the Sun. It's simple in principle but outrageously elegant in practice, and if you could slow it down, you'd see each step release a tiny packet of energy, a gamma-ray photon, along with a whisper of a neutrino that shoots straight through the universe, almost never interacting with anything. Right now, as you float here, trillions of those same neutrinos are passing through your body every second. Remnants of distant stars quietly slipping through your atoms like ghostly commuters. The scale of it all is dizzying. You reach out, but there's nothing to grasp, just the pulsing pressure of radiation, each photon bumping into the next on its long, chaotic escape from the core. If light had feelings, it might complain about the traffic. On average, a photon takes tens of thousands of years to travel from the center of the Sun to the surface, bouncing aimlessly through dense plasma, only to then sprint across space to reach Earth in a mere 8 minutes. Talk about bad commute to payoff ratio. You glance upward through layers of heat and energy so immense that distance becomes meaningless. The interior glows a molten gold, but the surface, if you can call that turbulent boundary a surface, shimmers like living fabric. Solar granules bubble and fade, each one a convection cell roughly the size of Texas, rising and falling in a slow hypnotic rhythm. It's mesmerizing the way the star breathes, expanding and contracting in steady cycles, always fueled by hydrogen's relentless transformation. A stray thought crosses your mind: if this process seems eternal, it's because it almost is. Stars like this can burn steadily for billions of years. The Sun, for example, is about halfway through its 10 billion year hydrogen phase. Historians still argue whether ancient cultures truly grasped the idea of stellar longevity, or simply imagined immortality, because stars seemed unchanging. The Egyptians called them the imperishable ones, and in a way they were right. Even when a star dies, its elements live on. Deeper in the core, fusion continues with an almost meditative steadiness. Each new helium nucleus sinks toward the center, slowly building up an inert core, while the outer layers keep burning hydrogen into helium. The process is so perfectly balanced that even a small change in temperature could cause catastrophe. If the core gets slightly hotter, fusion accelerates, creating more energy, which pushes the star outward and cools it again. If it gets cooler, gravity tightens its grip, raising the temperature until the balance is restored. It's like the universe invented its own thermostat and left it running on cosmic autopilot. There's a quirky tidbit that might surprise you. The fusion process inside a star is actually incredibly inefficient. Out of all the mass converted to energy, less than 1% becomes light. The rest remains locked in the atoms themselves. Yet that tiny fraction is enough to illuminate worlds and sustain life. Just 1 second of the Sun's output equals the energy used by humanity over 1 million years. It makes you wonder how small acts, tiny persistent changes, can illuminate entire lifetimes. The light surrounding you pulses in gentle waves, and you begin to feel as though you're floating inside a heartbeat, each surge of energy like a pulse of blood through a living organism. The star is alive in every meaningful way except consciousness. It eats, it breathes, it ages. The rhythm of fusion at its center is steady now, unhurried, each reaction a quiet promise that the balance holds. As you watch, you recall a fragment of history. In 1920, a young Arthur Eddington proposed that stars shine by fusing hydrogen into helium. He didn't have the math to prove it. Quantum mechanics hadn't fully bloomed yet, but he trusted intuition and physics enough to write it down anyway. Historians still argue whether Eddington's hunch was the boldest guess in astrophysics or just an inspired accident. Either way, he was right. 2 decades later, Hans Bethe and others worked out the details, revealing the proton-proton chain and its cousin, the CNO cycle, which dominates in heavier stars. Humanity had finally learned what every star already knew instinctively, that creation begins with a little pressure and a lot of patience. You drift toward the outer convection zone again, where energy from the core finally breaks free in visible light. Sunspots, flares, and swirling prominences twist across the surface, bursts of magnetism so vast they could swallow Earth whole. They're signs of turbulence, of plasma tangled by magnetic fields, but also signs of vitality. Every flare, every flicker, Every ripple is an echo of the ceaseless burning below. It's hard not to see beauty in it, the constant recycling, the unending change wrapped in stability. The hydrogen-burning phase of a star might seem monotonous, but it's the quiet engine that drives everything else. The warmth of a sunrise, the gentle light reflected off a leaf, the glow of a campfire. All of it traces back to fusion like this, somewhere, long ago or right now. Before you leave, you glance down one last time through the blinding heart of the furnace. You can't quite look directly. It's too pure, too fierce. But for a heartbeat, you sense the symmetry of it all. Gravity squeezing, heat expanding, light escaping, balance achieved. It's not chaos. It's a slow, luminous meditation, written in plasma and pressure. And as you drift back from that blinding glow, you realize that in the grand story of the cosmos, this is still just the beginning. Stars haven't yet started their second act, but the stage is set. The hydrogen burns on steady as breath. Waiting for the moment when the fuel runs low and change must come, you're still adrift in that light-drenched serenity when you begin to sense something subtler beneath the brightness. A rhythm, a quiet tugging between two eternal opposites. The star, now mature and stable, exists because of an exquisite balance. Gravity pulling inward with desperate strength and radiation pushing outward with luminous defiance. It's like watching a cosmic arm wrestle where neither side ever quite wins. You hover there, feeling the tension ripple through the plasma, and realize that if either force gained even the slightest edge, everything would unravel. The gravity that once birthed the star is still here, constant and unforgiving. It tries to collapse everything back toward the center, to return the universe to stillness. But every atom inside the core fights back, not out of rebellion, but out of heat. The energy from fusion pushes outward, an invisible counterweight to the star's own self-destruction. Together, they hold the structure steady, a perfect stalemate that can last for billions of years. You might think of it as serenity, but it's more like tension, frozen in motion. If you could pause the universe and listen closely, you'd hear the faint hum of this equilibrium. It's not bengo exactly, it's a low, thrumming resonance, like the hum of distant power lines stretched across time. Even the sun and your familiar neighborhood star hums this way, vibrating in subtle pulses that scientists measure to map its interior. There's poetry in that, the universe singing itself submissible. You drift closer, peering down into the layers again. The deeper you go, the more intense the pressure becomes, and the more you can feel the tug of war. Gravity doesn't quit, it's tireless, always reaching inward, while radiation constantly pushes back. In a way, this balance is the universe's first example of self-regulation, a cosmic blueprint for homeostasis. It's the same principle that keeps ecosystems balanced, lungs breathing, hearts steady. Even in the abyss, the same physics applies. There's a historical echo in this idea. Back in the early 20th century, before fusion was fully understood, astronomers debated endlessly about how stars could stay stable for so long. Some argued that they must be powered by gravitational contraction alone, others by mysterious unknown elements. Historians still argue whether it was Arthur Eddington's stubborn confidence or Cecilia Payne-Gaposchkin's brilliance that truly cracked the code. Payne-Gaposchkin, working in 1925, discovered that stars are made mostly of hydrogen and helium, an insight so bold that her own advisor told her not to publish it. She did anyway. Decades later, her error became the cornerstone of astrophysics. So yes, stars burn hydrogen, but it took human persistence to realize that truth. Back inside the star, the balance continues. You can imagine the pressure gradient like a series of invisible hands pressing inward and outward, each one perfectly matched by its neighbor. Radiation pressure comes from the very photons born in the core, their frantic motion pushing against matter. Gravity, ever jealous, pulls back harder. The result is stillness through struggle, something that feels strangely familiar. You drift outward again, and near the surface where the star's light spills into the void. Up close, the photosphere isn't smooth or calm. It's a roiling ocean of plasma, boiling with convection currents that rise and fall in bright golden cells. Each one lasts only minutes before collapsing back inward, replaced by another bubble of heat. It looks chaotic, but it's part of the same balance. Energy escaping, gravity restraining, the system breathing in slow, silent rhythm. You notice sunspots, those darker patches that freckle the surface. They're cooler regions where magnetic fields twist so tightly that they choke off convection, creating temporary shadows on the star's skin. Some are larger than Earth itself. These spots come and go in 11-year cycles, a solar heartbeat that ancient civilizations tracked long before telescopes existed. The Chinese astronomers of the Tang dynasty, for instance, recorded them as black vapors crossing the sun, long before Europe even knew what telescopes were. Historians still argue whether those early records helped to spark later advances in celestial prediction, or were simply curiosities scribbled in old scrolls. Either way, the sun has been spotted and studied for thousands of years. Its stability our reassurance, its storms our warning. From your vantage, the star's light is steady, but you know the illusion hides constant turmoil. The balance is dynamic, maintained moment by moment. When the outward flow of energy from fusion matches the inward crush of gravity, the star lives in perfect equilibrium, a main sequence star burning bright and calm. But if that balance falters, the consequences will be spectacular. You drift to the edge of its glowing limb, where light fades into blackness. Here, radiation pressure begins to thin, and gravity rules almost unopposed. The star's mass curves space-time itself, a gentle dent in the universe. You can almost feel that curvature, as though space bends slightly beneath your awareness. In heavier stars, that curvature becomes more extreme, light bending around the surface like a mirage. It's beautiful, in a kind of quiet, dangerous way. A thought flickers through your mind. Maybe the universe itself lives on balance. The galaxies expand, gravity pulls, dark energy pushes, and everything settles temporarily into harmony. Stars are just microcosms of that grand equation. It's humbling to realize that the same forces that shape entire galaxies are also at play in every atom of your own body. You too are a kind of equilibrium. Pressure and resistance, expansion and collapse, light and weight. A quirky bit of trivia comes to mind. In 1970, astronomers detected tiny oscillations in the sun's diameter, just a few kilometers wide, that correspond to internal pressure waves. They called them P-modes, and they are essentially sound waves rippling through the solar interior. The sun, in other words, rings like a bell. If we could hear it directly, the tone would be deep, far below human hearing, but constant. The universe doesn't just hum, it vibrates with the memory of its own balance. You linger for a while longer, caught between awe and quiet fear, because balance never lasts forever. Even now, the star's fuel is finite, and one day the inward pull of gravity will win. But for now, the symmetry holds, a perfect stillness born of struggle. It's strange how peaceful tension can be when both sides refuse to give up. And as you turn away, drifting outward into the velvet dark, you carry that lesson with you. Equilibrium isn't the absence of conflict, it's the mastery of it. The star before you no longer feels like a newborn, or even a reckless youth. It has settled into the long, steady rhythm of its main sequence life. You drift beside it, close enough to feel the hum of fusion through space and sense that everything about this phase is endurance. An era defined by patience rather than drama. This is the great middle age of stars, when they burn hydrogen calmly decade after decade, millennium after millennium, shaping the chemistry of galaxies with quiet persistence. The cosmos, it turns out, is not built on explosions and chaos alone, but on this gentle consistency, the slow heartbeat of hydrogen turning to helium, one fusion at a time. You take in the sight of the stellar neighborhood around you, red dwarfs glimmering like dying embers, blue-white giants flashing with fierce intensity. All of them are bound to the same rules, yet each plays the main sequence differently. The red dwarfs, smallest of the bunch, sip their hydrogen delicately, burning so slowly that they could live for 1 trillion years, far longer than the universe has existed so far. They are cosmic introverts, dim and unhurried, glowing faintly but faithfully. By contrast, the massive blue stars are the drama queens of the universe, devouring their fuel in a few short million years, blazing so brightly that they outshine entire clusters before collapsing in the spectacular self-destruction. You can almost hear them bragging about it. Burn fast, die young, leave a supernova behind. Somewhere in between sits the familiar yellow warmth of our own sun, a middleweight, living a stable 10 billion year existence. It's not the biggest or the brightest, but it's reliable, the cosmic equivalent of a workhorse that quietly powers the conditions for life. Historians still argue whether early civilizations worshipped the sun purely for its warmth, or whether on some instinctual level they recognised that it was the only reason Earth could exist at all. Either way, when they built temples aligned to solstices or carved golden discs into their altars, they were paying homage to this same main sequence serenity you're witnessing now. Drifting closer, you peer through the churning photosphere. The outer layers shimmer like molten honey, streaked with convection currents that rise and fall in slow motion. Each granule, each flicker of brightness, marks the journey of energy that began deep in the core millions of years ago. A single photon's life here is absurd, born in a violent fusion trapped for eons, then finally released to dash across space at light speed. The contrast is staggering and somehow poetic. All that waiting, all that wandering just to shine for 8 minutes on a patch of ocean, or the curve of your cheek on a warm afternoon. You shift your gaze to the cluster surrounding this star. The main sequence, if you could plot it, would form a beautiful curve on the Hertzsprung-Russell diagram, a chart that astronomers use like a cosmic family portrait. On it, every star finds its place, determined by temperature and luminosity. Cool, red, and faint on one end, hot, blue, and brilliant on the other. It's one of those rare scientific tools that's both practical and poetic, a snapshot of stellar evolution frozen in colour and light. The first version was plotted in the early 1900s, and historians still argue whether Einar Hertzsprung or Henry Norris Russell deserves more credit for its creation. It's a debate that's endured more than a century, though the stars themselves, indifferent as ever, just keep burning. You move toward a red dwarf star now, its glow dim but steadfast. It feels different, more intimate, quieter, as if it doesn't need to prove anything. Its fusion process is slow, almost meditative. Because of its low mass, convection stirs its entire interior, recycling hydrogen so thoroughly that no part of it is ever wasted. Unlike larger stars that will someday form dead helium cores, red dwarfs can burn all their fuel evenly, ensuring they live practically forever. In 1 trillion years, when brighter stars are long gone, red dwarfs will still shine faintly in the dark, whispering reminders of a more vibrant past. Then you swing past a blue supergiant, and the tone changes completely. The light hits you like a physical force, dazzling, sharp, and almost violent. This star lives fast and burns with 10,000 times the energy of the sun. Inside, fusion races through hydrogen so furiously that equilibrium becomes a delicate balancing act. Its surface temperature might exceed 30,000 degrees, and its winds strip away mass at terrifying rates. You can feel the tension, the restlessness of a life that knows it will be short. If the sun is a long novel, this one's a brilliant poem that ends halfway through a sentence. You float between them, between the eternal ember and the doomed inferno, and begin to see the main sequence as a cosmic spectrum of temperament. Each star, no matter its colour or size, exists in that same fragile balance you witnessed earlier. Yet how they live that balance defines everything that follows. What elements they'll forge, what remnants they'll leave, whether they'll end as gentle dwarfs or cataclysmic supernovae. It's like watching 1 billion lives unfold in parallel, all governed by the same simple laws of physics, but each with its own destiny. Here's a quirky bit of trivia for you. If you replaced the sun with a blue giant of equal mass, impossible, but imagine, it wouldn't just light Earth, it would sterilize it instantly. Its radiation would fry every molecule of DNA, leaving nothing but glowing rubble. The sun's calm golden temperature isn't just pleasant, it's a sweet spot between chaos and extinction. That's the gift of being average in a universe that rewards moderation. As you drift further out, you notice something faintly melancholy about the main sequence. It's stable, yes, but stability is only ever temporary. Deep inside, helium continues to build up, forming a dense core that can't fuse yet. One day, when the hydrogen runs low, gravity will start to tip the balance again, and this star will have to change. But for now, the calm persists, a long inhale before the inevitable exhale. You linger there, suspended between the fierce blues and the soft reds, feeling the heat of their fusion against your face and the cool vacuum of space behind you. The universe feels almost human in its pattern. Birth, balance, decline, each star a biography written in plasma and light, and as you drift among them you realise the truth of it. There's beauty in the middle chapters too, in the long, slow burning of a life that neither rushes nor fades too soon. Time folds around you as you hover near the star. The light that once seemed steady now carries a subtle tremor, a whisper that something inside is beginning to change. Billions of years have passed in what feels like seconds to you, and this once balanced main sequence star has reached the end of its calm. The hydrogen in its core, the fuel that kept gravity in check, is nearly gone. Deep inside, the equilibrium begins to falter. Fusion still burns in the outer layers, but the center has grown dense and exhausted, filled mostly with helium ash. You can feel the shift like a slow heartbeat stumbling out of rhythm. The long middle age of the star is ending, and what comes next is anything but peaceful. The collapse begins quietly. Gravity, that patient artist you met before, tightens its grip again. Without the steady outward pressure from hydrogen fusion, the core starts to contract. As it shrinks, it heats up more fiercely than ever, and that heat seeps into the surrounding layers. Hydrogen in those outer shells ignites in renewed fury, creating a burning shell around the core. The result? The star swells outward, its outer layers ballooning into space like a glowing red mist. From a serene yellow sun, it transforms into a bloated red giant. You drift back instinctively as its surface expands past the orbit where Earth once circled. It's no longer a quiet hearth. It's a bonfire too big for its own comfort. You watch as the colour deepens. The surface cools slightly because it's now so vast that its heat spreads thin, giving it that reddish hue, yet inside things are hotter than ever. Temperatures in the contracting core soar to around 100 million degrees, hot enough to spark a new kind of fusion. This is the triple alpha process, where 3 helium nuclei alpha particles combine to form carbon. It's a beautiful bit of cosmic chemistry. Helium, once the byproduct of hydrogen burning, becomes the new fuel. You can almost hear the universe chuckling softly, as if saying, "Nothing goes to waste here, Hilda." Helium fusion doesn't begin gently. It's more like a cosmic panic attack. For stars similar in size to the Sun, the helium core is so dense that electrons are crushed into a degenerate gas, a state of matter where pressure no longer depends on temperature. So when helium fusion finally ignites, there's nothing to regulate it. The result is a brief furious burst called the helium flash. In just a few seconds, the star releases energy equivalent to billions of hydrogen bombs, though the surface barely notices. The violence is hidden deep within. You feel it reverberate through the stellar layers, a single pulse of transition, a star clearing its throat before beginning its final song. Here's a quirky bit of trivia. The triple alpha process produces not only carbon, but a bit of oxygen too, depending on how long it continues. The balance between those two elements determines the chemical flavour of everything that follows. Too much carbon, and the universe would favour soot and graphite. Too much oxygen, and it would be an endless ocean of rust. Historians still argue whether Fred Hoyle, the British astrophysicist who predicted the exact energy level needed for carbon formation, truly believed the fine-tuning implied divine intention, or whether he was simply marvelling at coincidence. Either way, without that exact resonance, an almost miraculous alignment of physics, you and I wouldn't exist. As the red giant expands, its outer layers grow tenuous, like the atmosphere of a dying breath. You could fly through them without resistance, yet they glow with an inner light, illuminated by the searing heart within. You drift through the haze, watching convection cells rise and burst, each one the size of continents. The surface seems to boil in slow motion. Occasionally, bright flares arc outward as magnetic fields snap and reconnect. It's chaotic, unpredictable, but strangely elegant, like a candle flame caught in slow dance. You look outward and notice how the once dominant star now casts a softer light, red and melancholy. The space around it fills with dust, carbon dust, oxygen dust, the first solid grains that will one day drift into new clouds. You realize that this chaos is creative. Every puff of gas, every plume of vapor is seeding the future. Stars die messy deaths, but their mess is fertile. It's the universe's way of composting itself. You move closer to the core again, feeling the rhythm of helium fusion. Carbon begins to accumulate there, just as helium once did. But carbon, unlike hydrogen or helium, resists fusion unless the core grows even hotter. For stars like this, that's a boundary it can't cross, so it settles for transformation rather than transcendence. Eventually, the helium fuel will run out too, and when it does, the star will enter another wobbling phase of instability, its outer layers pulsating, expanding, and contracting like a tired heartbeat. You recall a story from the 18th century, Astronomers once called these flickering stars novae, thinking they were new stars being born. Historians still argue whether that linguistic mix-up slowed understanding of stellar death, but the irony is delicious. The word meant new, yet what they saw were old stars dying beautifully. Every red giant is a contradiction, decay that glows, death that shines. A gentle wind begins to blow from the star's surface, a stellar breeze carrying dust and atoms outward into space. You can almost touch it, feel the carbon brushing past like invisible ash. Over millions of years, this wind will strip the star of its outer layers, sending them drifting into space to form a glowing shell, a planetary nebula, fragile and radiant. But that's for later. For now, you hover within the red glow, watching the helium fusion pulse with quiet authority, realizing that creation and destruction have always been the same story told in reverse. The star's light washes over you, softer now, tinted with crimson melancholy. You can feel its warmth to me, though it's different, less urgent, more resigned. It's the warmth of something that knows it has done its part, that its future lies not in endurance but in giving itself away. And as you drift back through the expanding layers, through the slow dance of gas and light, you realize that even this ending is just another beginning waiting to unfold. You linger in the ruddy glow of the swollen giant, surrounded by a fog of shimmering dust and whispering winds of plasma. The star's expansion has slowed for now, though its surface still ripples like a restless sea. Deep within, the helium fusion you witnessed earlier burns steadily, transmuting helium into carbon and oxygen in a layered rhythm, each reaction echoing like a heartbeat beneath the haze. You can sense it, the slow, methodical creation of the elements that will one day shape worlds. Carbon, oxygen, the building blocks of every living thing, are being forged here in the dark furnace of a dying star. If hydrogen fusion was the universe's childhood, this is its adolescence, full of transformation, beauty and growing pains. You drift downward through the churning clouds until you reach the carbon-oxygen core. It glows like a molten pearl, dense and blindingly hot, a place where atoms crowd together in ways that would make Earth's metals seem like air. Each new atom formed is a work of art, a lattice of protons and neutrons bound by the strongest force known to physics, and yet the balance remains fragile. The core is inert for now, unable to fuse carbon. The temperature, though immense, hasn't reached the threshold needed to overcome carbon's stubborn stability. The star's energy, therefore, comes from the shell around the core, where helium still fuses with intensity. It's strange to think of this, energy radiating outward from layers rather than a single core. You imagine it like a cosmic onion, each shell performing its own alchemy, burning through different fuels. Hydrogen burns in the outer shell, helium in the next, and below that the carbon-oxygen core waits silently like a heart between beats. This layered structure, elegant and precarious, defines the star's final acts. It's here, in these few million years, that the chemistry of life begins to bloom. The scene feels oddly familiar, almost comforting. The reddish light filters through clouds of dust, creating an atmosphere reminiscent of a late autumn sunset. You half expect to feel wind on your face. The light catches on tiny grains of carbon drifting outward, tiny black flecks that glimmer as they spin. Some will clump together, growing into microscopic diamonds adrift in space. Yes, real diamonds, cosmic byproducts of stellar breath. A quirky fact that always makes people smile. Some meteorites found on Earth contain those same microdiamonds older than the Sun itself, proof that the universe has always been a little extravagant with its jewellery. You pause to admire the symmetry of it all. Carbon and oxygen, the very elements being created here, are the ones that later form the sugars in your blood, the proteins in your muscles, the air you breathe. You're not just watching cosmic history, you're watching autobiography. The atoms that will someday think, dream, and love are being sculpted before your eyes. Every star that passes through this phase writes the recipe for life into the universe. It's almost sentimental, if cosmic phenomena could be sentimental. In the outer regions, convection continues its wild ballet. Gigantic bubbles of plasma surge up from beneath, carrying freshly forged elements toward the surface. The star coughs them out through slow, steady winds. The space around it becomes enriched with carbon dust and oxygen gas, a delicate smog glowing under the star's fading light. Future generations of stars will be born from this dust, inheriting the chemistry of their ancestors. It's the grand recycling plan of the cosmos. Nothing wasted, everything reborn. You can't help but think of human ancestry, how every family traces its roots through generations. The stars do the same, though on a scale so immense it makes genealogies seem quaint. When astronomers analyse starlight, they can read those generations in the absorption lines, the fingerprints of elements in the star's atmosphere. Ancient stars show only hydrogen and helium. Younger ones, like the Sun, sparkle with metals, oxygen, silicon, iron. Historians still argue whether the phrase metallicity was first coined out of poetry or practicality, but it captures something profound. Stars age by getting heavier in spirit, richer in substance. Inside, the triple alpha process continues its quiet miracle. Helium burns into carbon through a precarious series of collisions. For a brief instant, two helium nuclei form an unstable beryllium-8 nucleus, one that would normally disintegrate in a heartbeat. But if in that fraction of a second, a third helium nucleus crashes in, it creates carbon. The odds are infinitesimal, but the sheer number of atoms ensures success. The universe, it seems, has always favoured persistence over probability. You drift closer to the inner core again, drawn by curiosity more than reason. The pressure there is immense, so immense that a teaspoon of this matter would weigh more than an entire mountain. Yet despite the density, there's still grace in its structure. Neutrinos slip out effortlessly, carrying away heat. Electrons dart through lattices of nuclei, holding the core in delicate balance. The star hasn't reached its breaking point yet, but you can feel it approaching. One day soon, even helium fusion will falter, and the outer layers will begin to pulse and shed, forming a planetary nebula so bright it could outshine an entire galaxy for a few weeks. Before leaving, you take in the sight one last time, the red giant's surface rippling, the wind carrying its essence outward in glittering streams. You think of the ancient Chinese astronomers who watched a bright red guest star appear suddenly in the sky in 1054, the supernova remnant we now call the Crab Nebula. Historians still argue whether they understood they were witnessing stellar death or simply recorded it as divine omen. But they must have felt the same awe you do now, that the universe writes its endings in light, not silence. The red glow softens, and you realise this stage, though transitory, is vital. Stars must age, must grow unstable, for the elements of life to escape their gravity wells. Every heartbeat, every fusion, every dying ember, it's all part of one continuous act of giving. You float among the drifting carbon dust, watching it settle into the void like embers cooling after a long fire. Somewhere far in the future, these atoms will reassemble into something new, something curious enough to look back at the stars and wonder where it came from. And the answer, whispered through cosmic time, will always be the same. Right here, the red giant flickers like a dying ember in the night of the cosmos. Its beauty is almost painful now, a reminder that even the brightest lives eventually dim. You hover far enough away to see the full expanse of its swollen form, the surface trembling as if unsure how to hold itself together. The crimson light is hauntingly gentle, and yet within that soft glow, something irreversible is happening. Deep inside, the nuclear fire that once drove creation is nearing its limit. The star's core, dense, stubborn, and unyielding, has become dominated by iron. And in that single element lies the quiet, inevitable stop sign of the universe. Iron, as it turns out, is the point where fusion's generosity ends. Up to this moment, every fusion reaction released energy, binding lighter elements into heavier ones and giving the star its radiant life. But iron is different. Its nucleus is so tightly bound that fusing it absorbs energy instead of releasing it. The cosmic economy no longer works in the star's favour. The moment iron dominates the core, the star's internal bank of fuel is bankrupt. You can feel the tension building, gravity still wants to collapse the core, but there's no longer enough pressure from fusion to resist it. It's the final standoff between light and weight, and this time gravity will win. You drift inward, sensing the star's exhaustion. The layers above the core are still burning their respective elements, silicon, sulfur, magnesium, all in concentric shells, each one living only for a few frantic days or hours before exhausting its fuel. It's a frenzy, a last-minute rush of creation. In massive stars, these stages happen so quickly that the core becomes an onion of fire, every layer a record of nuclear history. The outermost shells still fuse hydrogen and helium, the inner ones carbon and oxygen, while the innermost shell churns silicon into iron. The pace is desperate. Billions of years of calm have condensed into a few heartbeats. It's here, watching this frantic layering, that you begin to understand why astronomers call this advanced burning. The star in its final moments behaves like an artist who senses the end of a masterpiece, furiously mixing colours, layering textures, leaving behind as much beauty as possible before time runs out. The core temperature now exceeds 3 billion degrees, hotter than anything your mind can truly grasp. The radiation here would vaporize entire planets, and yet the star's light remains strangely steady from afar. Its face hides the turmoil beneath. A quirky tidbit slips into your thoughts. The very concept of nuclear binding energy, the reason iron ends fusion, was first quantified in the 1930s. Scientists discovered that elements lighter than iron release energy when fused, while those heavier than iron release energy only when split apart. That's why stars build up to iron, and why humanity's most powerful creations, the atomic bomb and the nuclear reactor, work by breaking heavy elements apart. The symmetry is darkly poetic. Stars create light by joining atoms. Humans create it by tearing them apart. Historians still argue whether this realization humbled us or merely tempted us to imitate the stars. You move closer to the core and feel the suffocating weight of it. The iron center is now as dense as the nucleus of an atom, but it keeps shrinking, atom by atom. When gravity can no longer be resisted, the collapse will be catastrophic, an implosion so violent that it will momentarily outshine an entire galaxy. But for now, the star holds, trembling on the edge of the inevitable. The silence is deceptive. Feels like standing in a theatre just before the orchestra plays its final note. You trace the light outward through the layers. The outer shells, unstable and swelling, begin to pulse. Waves of pressure ripple outward, ejecting wisps of gas into space. Each pulse sends a shockwave through the surrounding nebula, stirring the cosmic dust like the breath of a giant. The star has become both creator and destroyer, giving life to the elements that will outlive it while sealing its own fate. There's something eerily human about its stubbornness. Even knowing it cannot continue, it keeps producing, keeps burning, refusing to fade quietly. You can't help but admire that defiance. The balance that once defined its long main sequence life is gone, replaced by chaos, but within that chaos lies purpose. Carbon, oxygen, silicon, its calcium, all forged here in its final acts. The same calcium that will one day harden bones and the same oxygen that will fill lungs. You realize you're watching your own origins compressed into seconds of stellar agony. The outer atmosphere begins to shimmer with instability. Flares and shockwaves ripple across the surface, ejecting plasma thousands of kilometers high. If you squint, it looks almost alive, breathing, trembling, waiting. The light flickers faster now, the rhythm uneven. The star is running out of layers to burn, out of reasons to keep its shape. Its core is now a ticking bomb of degeneracy pressure, supported only by electrons pushing back against gravity. When that final threshold is crossed, when even electrons can no longer resist collapse, everything will change in a fraction of a second. For a moment, you drift far enough away to see the star against the black canvas of the galaxy. It's one among billions, indistinguishable to a casual glance. No one looking from a distance could guess that inside history is reaching its climax. But you know, you can feel it, the unbearable compression of energy, the silence before the storm. You can almost hear the faint metallic whisper of iron settling into stillness. It's haunting the way the end looks so peaceful from afar. Perhaps that's always how endings appear, quiet until the light changes. You take one last look at the trembling red giant, its brilliance steadying for a final heartbeat. And you realize the next moment will rewrite everything. The laws of physics themselves are about to scream. The star has reached its limit, and the universe is sharpening its breath, ready to exhale. It begins in seconds, then in less than the blink of an eye, the star's entire core collapses. One moment, its heart is the size of Earth, the next, it shrinks to the scale of a city. Gravity, unchecked and ravenous, crushes the iron core inward at a quarter of the speed of light. Temperatures spike to over 100 billion degrees. You watch helplessly as atomic nuclei, those proud fortresses of protons and neutrons, crumble under the pressure. The electrons that once supported the star are forced into protons, merging to form neutrons, and in that instant, a flood of neutrinos bursts outward like a silent scream. The core becomes one massive neutron, impossibly dense, impossibly small. Everything the star has ever been, everything it has ever created, is now collapsing inward at once, and then the rebound. The inner core, having compressed to its absolute limit, stiffens like a spring and snaps outward. The infalling material slams against it, sending a shockwave rippling through the surrounding layers. You can almost feel it through space, the impact, the thunder of rebirth. The entire star detonates from within, releasing more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime. This is a supernova, the universe's loudest farewell. You float just far enough away to survive, though survive is relative. Space around you flares into pure white light, brighter than anything your eyes can bear. The star's outer layers are hurled into the void at thousands of kilometers per second, a blizzard of atomic debris scattering through the galaxy. Hydrogen, helium, carbon, oxygen, iron, all flung outward in a storm of radiance. For a moment, it's chaos incarnate. Glowing ribbons of plasma, shock fronts colliding, magnetic fields twisting into beautiful lethal knots. It's terrifying and sublime, a kind of violence that creates rather than destroys. You realize that what you're witnessing is not death but redistribution. The iron that stopped fusion now finds new purpose. The explosion's heat and pressure are so immense that even heavier elements form: nickel, gold, uranium, the rarest treasures of the cosmos. They flash into existence for the briefest fraction of a second before being swept away in the explosion. Somewhere far in the future, those atoms will drift together into a planet, a mountain, a bloodstream. The gold in a wedding ring, the iodine in your thyroid, the iron in your blood, they were all born in moments like this, in the violence of a dying star. Here's a quirky fact to make you smile amid the devastation. When astronomers first observed supernova 1987A, they found traces of freshly made nickel in its debris cloud. Over the following months, that nickel decayed into cobalt and then into iron, releasing light that kept the supernova glowing long after the explosion faded. The universe, in a sense, made its own nightlight to remember the event by. Historians still argue whether that discovery marked the true beginning of modern stellar nucleosynthesis, or whether the theory had already matured. Either way, the observation gave humanity something humbling. Proof that stars don't just die, they give gifts that last billions of years. You drift among the remnants, surrounded by beauty too fierce to last. Expanding tendrils of gas stretch for light years, shimmering in every colour imaginable. Blue from oxygen, red from hydrogen, green from sulfur. It's like watching the inside of a firework frozen in time. Each wave of debris carries with it the fingerprints of the elements inside, a cosmic message written in light. You reach out as a glowing filament passes by, and though you can't touch it, you can feel the energy humming like a note sustained on a universal chord. In the centre, where the star's core once burned, something new has formed. A neutron star, barely 20 kilometers wide yet heavier than the sun. It spins rapidly, its magnetic fields whipping charged particles into luminous beams that sweep across space like lighthouse lights. These are pulsars, the ticking hearts of dead stars. You can almost hear their rhythm, a steady, mechanical pulse, like the metronome of eternity. If the star had been even more massive, its collapse would have gone further still, forming a black hole, a point of no return where even light cannot escape. The difference between the two fates is measured in mere solar masses, but the consequences span universes. The energy around you begins to settle. The shockwave races outward, thinning into the dark. The temperature drops from billions to millions of degrees, and dust begins to condense from the cooling gas. Tiny grains of graphite and silicates, future stardust, form amid the wreckage. They drift outward, carrying with them the signature of this star's life and death. You realize that somewhere far away, another nebula is already forming, seeded by the remains of earlier explosions. This is how galaxies renew themselves, through death, through fire, through light. A strange calm follows. The blinding brightness fades into a ghostly glow, and for the first time you can see the aftermath clearly. It's beautiful, but it's also heartbreakingly empty. The space where a sun once blazed is now a hollow sphere of gas expanding into the void. You feel the absence as much as the presence, the silence after the music stops, yet in that silence lies the promise of new creation. The debris will mingle with interstellar clouds, sparking new collapses, new stars, new stories. The cycle never truly ends. You think about how ancient humans once feared comets and bright new stars in the night sky, calling them omens of doom. Historians still argue whether the guest star seen by Chinese astronomers in 1054 frightened or fascinated them, but they were witnessing exactly this, a star's final act, its ashes already on their way to becoming something else. Perhaps every myth about death and rebirth, from the phoenix to the cosmic egg, came from watching events like this. Stars die, but their death is always a beginning. You linger a little longer in the fading light, letting the enormity of it settle over you. The thought hits you quietly. One day, even the sun will follow this path, less violently perhaps, but inevitably. And when it does, its elements will scatter too, ensuring that something new will rise in its place. You're part of that pattern already, a small echo of an ancient explosion. It's not just poetry, it's physics. You are literally the universe learning to understand itself. The shockwave passes, the light softens, and the darkness returns, full, deep, and infinite. You float in it for a moment, weightless and awed, listening to the faint echo of a star's last breath as it dissolves into the long silence of space. The darkness that follows the supernova is not emptiness, it's aftermath. You float through a region of space still trembling from the blast, the ghostly shell of the explosion expanding around you like a giant soap bubble. The gas is cooling, slowing, coalescing into filaments that curl and twist in the faint light. They look fragile, almost delicate, yet they carry within them the entire periodic table, every element that will one day make worlds and beings. The star is gone, but its story has just begun again, told now in drifting dust and atoms seeking new purpose. You follow the path of one speck of debris, a carbon atom still vibrating with residual energy. It spins through the growing cloud, colliding, joining, separating. Over thousands of years, the shockwave slows, and the debris spreads across dozens of light years. The once solid heart of a star has become a whisper of elements drifting through the interstellar medium. You realize that this is how the galaxy sustains itself. Every generation of stars dies so the next can be born richer, heavier, more complex. You can almost see the Milky Way breathing in and out, a slow cosmic respiration spanning billions of years. Among the cooling fragments, new structures begin to emerge. Dust grains collide and clump, forming microscopic seeds of future planets. They gather around hydrogen and helium gas, drawn together by gravity's patient pull. The remnants of one star now serve as the foundation for countless others. You can sense that another stellar nursery will soon bloom here, perhaps even one with planets capable of oceans and skies. The universe is recycling itself before your eyes, turning destruction into creation. There's something quietly comforting about this. Death here is never final. Every atom ejected in that blast continues on its journey, reshaping itself again and again. The calcium in your bones, the phosphorus in your DNA, the gold in a ring, they were all flung into being by an ancient supernova like this. It's not metaphor, it's arithmetic. The periodic table is a eulogy written by dying stars. You glance toward the edge of the supernova remnant, where light and shadow play across wisps of gas. Over centuries, those glowing tendrils will fade into invisibility, blending into the surrounding interstellar medium. But the material won't vanish. It will enrich the galaxy's next wave of clouds, the nurseries where new stars form. Historians still argue whether the idea that we are made of star stuff, popularized by Carl Sagan, originated purely from poetic intuition or from the earlier work of Fred Hoyle and Margaret Burbidge, who mathematically mapped stellar nucleosynthesis in 1957. Either way, the phrase endures because it's true, and because it makes our existence feel both impossible and inevitable. You drift closer to the heart of the explosion. The neutron star remains, a dense spinning ember, flashing with a rhythm as precise as a clock. Every rotation sends twin beams of radiation across space. You let one sweep past you, and for an instant you feel the intensity of it. A narrow cone of energy so sharp it could vaporize planets. Yet even this remnant will fade in time. The neutron star will slow, its light will dim, and the surrounding nebula will dissolve into the galactic haze, but the matter it released will continue to travel outward, spreading the legacy of its parent star across light years. If you could fast forward a few million years, you'd see this region transformed into a calm molecular cloud. Hydrogen molecules would mingle with heavier atoms, forming cool, dense pockets of gas. Within those pockets, gravity would once again begin its ancient work, pulling material together until new protostars ignite. You imagine the scene, bright points flaring to life in the same place where another once died. It's a cosmic relay race, each star passing the baton of creation to the next. There's a strange, almost spiritual elegance to that continuity. Stars are not isolated events. They are chapters in an unending book. You can trace the lineage of every atom in your body through this molar process, each one having lived through countless stars, explosions and clouds. Even the water you drink, 2 hydrogen atoms bonded to 1 oxygen, carries the fingerprints of both the Big Bang and stellar death. The universe doesn't create waste, it only rearranges itself. You pause and let the weight of that truth sink in. All around you, the debris moves silently, a slow dance of rebirth. From the chaos, order begins to return. Magnetic fields thread through the gas, guiding particles into filaments. Regions of density form, glowing faintly where starlight from elsewhere scatters through the dust. You can almost see the faint outlines of new solar systems waiting to be born. In one of those systems, perhaps billions of years from now, a blue planet will orbit its star and wonder about its origins. That curiosity, your curiosity, was born here. A quirky aside floats into your mind. In 20-pound time, astronomers detected a kilonova remnant so rich in heavy elements that it contained an estimated Earth's worth of gold. Just one cosmic explosion and an entire planet's treasure was born. It's hard not to laugh at the irony. Humanity mines gold as if it's precious, but the universe makes it by accident, scattering it like glitter after a party. It's a humbling thought. What we hoard, the cosmos casually creates and throws away. You drift outward now, beyond the edge of the fading nebula. The light dims, replaced by the cool black of open space. The silence is immense, but not empty. Within it, you sense the hum of potential, the quiet before the next ignition. You take one last look at the glowing remnant behind you, its gases spreading thin, its light fading into the distance. Somewhere within that expanding dust lies the blueprint for new life, new worlds, and perhaps new minds that will one day wonder at their own origins. As you turn away, a single particle of light from the explosion brushes past your cheek. It's ancient now, stretched and softened by the passage of time, but it carries the memory of that star's final breath. You realize that even light, in its endless journey to Moon, is part of the same Srudis, to move forward, to illuminate, to carry history across the void. You smile in the dark, knowing that what was once a supernova will one day be starlight again. You float through a quieter corner of space now, where the scars of the explosion have softened into a misty glow. The ferocity of the supernova has long faded, and in its place linger only the ghosts of pressure waves and the last whisper of radiation. At the centre of it all lies the remnant, a neutron star, impossibly dense and eerily perfect. You draw closer, feeling the subtle tug of its gravity, a presence that seems to bend not just matter, but your sense of scale itself. In a way, this object is what remains when nature has done its most extreme experiment and kept the results. Up close, the neutron star looks deceptively calm. Its surface is smooth and dark, shining faintly with residual heat, but beneath that quiet lies chaos. Every cubic centimetre contains more mass than Mount Everest, all packed into neutrons so tightly that atomic boundaries no longer exist. The magnetic field here is unfathomable, trillions of times stronger than Earth's, and it cracks space like invisible lightning. Occasionally one of those magnetic fractures releases a burst of energy so violent that it travels across galaxies, lighting up distant instruments on Earth. Astronomers call them magnetas, the drama queens of neutron stars. One such flare in 2004 briefly ionized part of Earth's atmosphere from 50,000 light-years away. You chuckle softly, talk about long-distance communication. You watch the star rotate faster than a blender blade. Some neutron stars spin hundreds of times per second, each rotation firing beams of radiation from their magnetic poles. When those beams sweep across your position, you see a flicker of light, regular, rhythmic, hypnotic. This is a pulsar, the universe's own metronome. You can almost tap your finger to its tempo, a steady beat that will persist for millions of years, long after your own heart has stopped. Historians still argue whether Jocelyn Bell Burnell, the astrophysicist who first detected pulsars in 1967, received her due credit for the discovery, or if the Nobel Committee's oversight remains one of science's quieter shames. Either way, her little green men signal turned out to be the heartbeat of collapsed stars. You drift closer, careful not to cross the point where its gravity would stretch you thinner than starlight. The neutron star's crust is unlike anything else in existence, made of exotic matter, crystalline yet fluid, harder than diamond but trembling with quantum vibrations. Beneath that surface lies a soup of neutrons swimming in a sea of superfluid particles, so frictionless that if it were poured into a cup it would spin forever. The entire object is the size of a city, yet it contains more matter than the sun. If you could scoop up a teaspoon of it, it would weigh billions of tons, enough to crush a skyscraper in an instant. The mind can't truly grasp that, so you settle for wonder. You look around, tracing the faint ring of debris that still circles the neutron star. The expelled gas forms a shimmering halo, slowly dissipating into the interstellar medium. Occasionally, a fragment falls back toward the remnant, releasing a flash of X-rays as it collides with the surface. It's like watching sparks fly from cooling embers, reminders of a fire that once consumed the sky. In time, even those sparks will fade, and the neutron star will cool into invisibility, a dead ember adrift in the galactic dark. Yet not all remnants fade so quietly. Some neutron stars have companions, other stars bound to them by gravity. When the surviving partner strays too close, the neutron star begins to steal from it, siphoning gas in a whirlpool of light and radiation. You spot one such pair nearby, a binary system locked in a gravitational embrace. The neutron star's accretion disk glows with fierce blue energy, spinning faster than thought, while streams of matter arc between the two stars like glowing threads. It's chaotic, destructive, and oddly intimate, an endless dance of taking and giving. A quirky bit of trivia crosses your mind. If a neutron star collides with another neutron star, the resulting explosion, called a kilonova, can forge even heavier elements than a supernova, including gold, platinum, and rare earth metals. In 2017, astronomers actually witnessed one for the first time through both light and gravitational waves, confirming a prediction Einstein made a century earlier. Historians still argue whether that event marked the beginning of a new era of multi-messenger astronomy, or simply gave humans a bigger sense of cosmic humility. Either way, it proved that even in death, stars continue to create. You move outward again, leaving the binary's violent glow behind. The starscape around you is rich with history, each point of light a survivor or successor of similar explosions. Some are young, still forming planets. Others are old, dim, and fading. The galaxy's arms spiral outward in a slow, glittering curve. Built from countless generations of such lives and deaths, it's easy to forget, drifting here, that everything beautiful in the night sky is made possible by endings like the one you've just witnessed. The neutron star's faint pulse continues behind you, ticking steadily through the void. Its rhythm is oddly comforting, a reminder that even the most extreme transformations follow patterns. Gravity collapses, matter condenses, energy bursts, and from that chaos comes order, temporary, fragile, but undeniably real. You begin to think of these remnants not as tombstones but as milestones, markers of the universe learning how to make itself over and over again. You glance back one last time. The pulsar's beam sweeps past, catching you in its ghostly light, and for a moment you feel an impossible connection. The same physics that collapsed that star governs the atoms in your bones. The same gravity that crushed its core binds you to the planet you call home. You realize there is no out there and in here. The distinction is poetic, not physical. The universe breathes through every particle of you and through every dying star that gives you the elements to exist. The pulse fades. Space grows quiet again, but it's not a lonely quiet. It's a full silence, rich with potential. You turn toward the distant glow of another nebula, the birthplace of new stars forming from the ancient dust. The cycle continues, indifferent yet oddly benevolent. As you drift toward that newborn light, you carry the echo of the neutron star's rhythm with you, a cosmic lullaby reminding you that endings are only pauses between creations. The neutron star's pulse fades into the distance as you drift onward through the galactic haze, following the invisible trails of dust and gas left behind by generations of stellar deaths. Ahead of you stretches a vast molecular cloud, dark, cold, and quietly alive with potential. This is where stars are reborn, where the scattered atoms of old suns gather again under gravity's patient touch. You move through it slowly, your vision filled with soft shadows and faint glimmers. Each particle of dust carries history, the calcium from one ancient star, the carbon from another, the oxygen that will one day fill a living lung. The airless dark hums with quiet purpose. You are floating through the universe's recycling center. It's a beautiful kind of irony. Destruction fuels creation. Every supernova, every dying red giant contributes to the chemical richness of this nebula. Hydrogen and helium still make up most of it, but now there are trace amounts of heavier elements, what astronomers call metals: iron, silicon, nitrogen, neon, sulfur. Tiny specks that make the difference between barren simplicity and complexity capable of thought. You can almost see the galactic genealogy written here. Early stars were pure hydrogen and helium, burning quickly and dying young. Later generations inherited these heavier elements, becoming more fertile, more capable of forming planets and eventually life. You drift through a dense pocket of the cloud where gravity has already begun its quiet work. Wisps of gas curl inward, forming filaments that twist like veins across a cosmic body. Inside those filaments, knots of density form, the first hints of new stars. Radiation from nearby supernovae nudges the process along, compressing the gas until it collapses on itself. Everywhere you look, there's motion, slow but relentless. It's like watching a forest regrow after a wildfire, each seed carrying the memory of the blaze that made room for it. The concept of stellar population flits across your mind: population 1, the 2 and 3 stars, the 3 great generations of cosmic ancestry. The first, made almost entirely of hydrogen, are long gone, their lives ending in massive explosions that seeded the universe with metals. The second and third generations, the ones like our Sun, inherit that enrichment, each one containing a little more complexity than the last. Historians still argue whether the classification's terminology came from physics or human vanity, the impulse to sort the cosmos into family trees. Either way, it helps us see the galaxy as a living organism, renewing itself endlessly. You glide deeper into the cloud where light barely penetrates. The temperature here is only a few dozen degrees above absolute zero, and yet this frigid darkness is full of chemical whispers. Molecules form on dust grains, water, ammonia, formaldehyde, even simple sugars. These are the building blocks of life, forming not in laboratories but in the coldest corners of the galaxy. You touch one icy dust mote and imagine it drifting for millions of years until one day it becomes part of a new planet, a new ocean, or a new cell. The thought feels oddly comforting. The future of everything begins here. In the stillness, you move toward a cluster where the gas glows faintly from the ultraviolet light of nearby young stars. Their radiation sculpts the surrounding material into towers and ridges, pillars of creation, much like the ones in the Eagle Nebula. You can see new stars embedded within, hidden in cocoons of dust, their faint flickers breaking through like fireflies behind fog. Each one represents the rebirth of matter that once belonged to countless other stars. The cycle is flawless in its efficiency, almost spiritual in its repetition. A quirky tidbit drifts into your mind. In 1995, astronomers using the Hubble Space Telescope detected proplyds, protoplanetary disks, within the Orion Nebula. These were the first confirmed glimpses of solar systems forming in real time. Each glowing oval was a baby sun surrounded by a swirling disk of dust, waiting to give birth to planets. Historians still argue whether that discovery marked the true dawn of exoplanet science or merely confirmed what theory had long predicted. But the wonder was universal. Humans were finally watching the same process that once created Earth. You glide between 2 such disks now, their glowing edges spinning gracefully. You can sense the tug of gravity shaping them, rings within rings, turbulence giving way to structure. The central stars are still young, their light unsteady, their surfaces boiling with energy. Yet around them, dust grains are colliding, sticking, merging. Pebbles become rocks, rocks become boulders, boulders gather into protoplanets. It's slow, messy, and full of accidents, but out of it will come systems of astonishing harmony. You wonder how many of these will host oceans, continents, atmospheres, and whether billions of years from now any of them will look up and wonder about their own origins. You pause and look back over your shoulder, tracing the invisible line from those forming planets to the supernova you left behind. The gas that now builds these new worlds was once part of that dying star's core. The iron in their future mountains, the oxygen in their potential atmospheres, even the carbon that may someday shape their life. It all began as debris in a stellar grave. The cycle feels endless, but not monotonous. Each iteration adds something new, a subtle complexity, a step closer to consciousness. Drifting through this quiet nursery, you realize that galaxies are not just collections of stars, they're ecosystems. They inhale and exhale through generations of birth and death, their spiral arms like lungs breathing light. The Milky Way has been doing this for over 13 billion years, and it will continue long after you're gone. You reach out, metaphorically, to touch that rhythm, to feel yourself as part of the pattern. You are, after all, the product of these same clouds, the same chemistry, the same starlight. A faint breeze of radiation brushes past you, carrying warmth from a newborn star. It feels like a whisper from the past and the future all at once. You breathe it in, not literally, but emotionally, and it fills you with an odd sense of peace. The supernova's violence, the red giant's grief, the neutron star's pulse, they were all preludes to this gentle rebirth. Life, it seems, was never about permanence. It was always about transformation. The darkness ahead deepens, dotted with 1,000 new points of light. Each one is a promise, a beginning written in hydrogen and dust. You smile, realizing that this journey, the rise and fall of stars, is the closest thing the universe has to a heartbeat. And as you drift onward through the cool silence of the nebula, you feel that pulse in your chest, soft and steady, as though the cosmos itself is breathing with you. You emerge from the haze of the molecular cloud and into a familiar light, golden, warm and steady. It's your own star now, the sun, shining with the calm confidence of middle age. After all that cosmic violence, its serenity feels almost intimate. You float above it, watching the surface ripple and churn, waves of plasma rising and falling in convection cells the size of continents. Each flicker, each shimmer, is a whisper from deep within, a steady hum of hydrogen fusion that has burned for 4.6 billion years. You know this star better than any other, yet somehow, seeing it now, you realize how deeply it carries the legacy of all that came before. Every atom in the sun tells a story. Its hydrogen and helium trace back to the Big Bang itself, the universe's first breath. The carbon, oxygen, nitrogen, silicon, and iron came from earlier generations of stars, those same supernovae and red giants you've travelled through. The sun is not new, it is an heirloom, a mosaic of rare recycled stardust inherited from thousands of cosmic ancestors. You can almost imagine them whispering through its light, a chorus of long-dead suns humming in resonance. You are looking at the family tree of the universe condensed into a single blazing sphere. You drift closer, feeling the faint pressure of the solar wind brushing against you. Streams of charged particles flow outward in all directions, carrying bits of the sun's atmosphere deep into space. Some of that plasma will reach Earth in a few days, painting the polar skies with auroras. Some will drift farther into the interstellar medium, mingling with the same dust that once gave birth to this star. The cycle continues, seamless and patient. The universe never stops exchanging pieces of itself. The sun's light pulses gently, its surface alive with motion. Sunspots, dark regions of magnetic turbulence, appear and fade in 11-year cycles, a quiet heartbeat that influences everything from satellite signals to climate patterns on Earth. You can see one forming now, a shadow stretching across the bright photosphere like a bruise. It looks small from here, but it could swallow Earth twice over. Flares burst from its edges, arcs of plasma leaping thousands of kilometers high before falling back in fiery ribbons. It's beautiful, dangerous, and oddly comforting, like watching ocean waves that could crush you but don't. Here's a bit of history that floats through your mind. In 1859, the sun unleashed a flare so powerful it electrified telegraph systems across the world. The Carrington event, they called it, the first recorded solar storm. Historians still argue whether that moment truly marked humanity's awakening to the sun's influence or if it was dismissed as a curious inconvenience. Either way, it proved a humbling truth. The same light that nurtures life can also occasionally remind us who's in charge. You turn your attention to the solar core, invisible yet vital. There, at 15 million degrees, hydrogen atoms merge into helium, releasing energy that slowly migrates outward over hundreds of thousands of years before finally emerging as sunlight. That light, the one touching your face right now, may have begun its journey before mammals even walked the Earth. Every photon is an ancient traveller, and when it reaches your skin, your eyes, or a leaf on a tree, it completes a cycle that began in the heart of a collapsing nebula. The sunlight that feeds a forest today may have been born when the first continents were still molten. The Earth drifts into view, a small blue marble orbiting faithfully within the sun's gentle embrace. You can almost feel the warmth that bathes it, the balance that makes it possible for oceans to exist, for weather to flow, for life to bloom. It's a fragile equilibrium, held together by just the right distance, just the right luminosity. You marvel at how easily it could have gone differently. If the sun were a little larger, its lifespan would be shorter, its heat unbearable. If smaller, it might never have ignited. The odds are cosmic, yet here it is, the perfect balance between gravity and light. You drift closer to Earth and let your gaze linger on its surface. The atmosphere glows faintly blue, scattering sunlight into softness. You know that the air itself, oxygen, nitrogen, carbon dioxide, exists because earlier stars created those elements. Every breath, every drop of water, every blade of grass is a direct consequence of stellar alchemy. The atoms in a single exhalation have cycled through stars, oceans, and organisms for billions of years. There is no boundary between you and the sun, only continuity. A quirky tidbit makes you smile. In 1957, a group of astrophysicists, Burbage, Fowler, and Hoyle, published a landmark paper titled Synthesis of the Elements in Stars. It laid out the full process of stellar nucleosynthesis, showing how all elements, including those in our own sun, came to be. Historians still argue whether that paper truly marked the moment humans understood the stars or simply caught up to what the universe had been doing all along. Either way, it was the first time we realised with mathematical certainty that our sun is part of a grander story, a link in an unbroken chain of creation. You move back again, letting the entire solar system fill your view. The planets circle gracefully, each one a fragment of the same dust that once drifted through a long-lost nebula. Mercury scorched, Venus shrouded, Earth vibrant, Mars waiting. Farther still, gas giants spin like marbled jewels, and beyond them comets trace long, icy ellipses, remnants of the sun's own birth cloud. It's a living museum of stellar heritage, every orbit a reminder that gravity never forgets where it began. For a moment, you close your eyes and listen. There's a rhythm here, soft and steady, the hum of fusion, the whisper of the solar wind, the faint murmur of planets in motion. It's the sound of a system in harmony, the kind of balance stars strive for and rarely maintain forever. The sun will one day grow old too, its hydrogen exhausted, its glow deepening to red, but that future feels far away. For now, it burns with purpose, a quiet sentinel watching over its creations. You drift one last time through its light, feeling its warmth as more than energy, its inheritance. You're not just orbiting a star, you're orbiting your ancestors. Every flicker of sunlight that touches your skin carries with it the memory of galaxies past. The sun is a reminder that even the smallest light in the universe contains the echoes of eternity. You linger near the sun, basking in its soft radiance, and begin to think about how humanity, small, curious, and stubborn, has tried to recreate what you're seeing. Down there, on that tiny blue world, we've spent decades attempting to bottle a star. Fusion research, the dream of making our own sun in a machine, of mastering the same process that powers every beam of light in the sky, is almost poetic. Creatures made from stardust trying to ignite their origins anew. You drift back slightly, watching Earth turn below, and imagine the labs, the reactors, the scientists who've devoted lifetimes to coaxing atoms into that delicate, luminous dance. The contrast between the sun's effortless brilliance and humanity's painstaking effort makes you smile. You can almost hear the hum of those laboratories, tokamaks and accelerators humming with magnetism. Inside their donut-shaped chambers, hydrogen isotopes are heated to hundreds of millions of degrees, forming plasma so hot that even metal walls can't touch it. Magnetic fields twist and confine it, shaping it into a contained miniature sun. The goal is simple but monumental: to achieve sustained fusion, to turn hydrogen into helium and release pure energy without waste, without destruction. For now, it's still a promise hovering just out of reach. The irony, of course, is that stars do this naturally, effortlessly, without wires or funding or grant proposals. But humanity has never been content to watch from afar. Imitation is our favourite form of reverence. You drift closer to the planet, zooming in on glowing research facilities nestled in deserts and coastal plains. There's ITER in southern France, a multinational experiment built with the same cooperation once reserved for space exploration. There's the National Ignition Facility in California, where lasers the size of skyscrapers converge on tiny fuel pellets to spark fusion reactions. There's the Joint European Torus in the UK, now retired but still the proud ancestor of the next generation. Each one represents a step, a stumble, a renewed attempt to capture what the sun does without thinking. Historians still argue whether humanity's obsession with fusion is driven by scientific curiosity or cosmic nostalgia, a yearning to hold the same fire that made us. You pause to watch the aurora shimmering above Earth's poles, ribbons of green and violet dancing in the upper atmosphere. Those ethereal lights are the sun's own touch, charged particles from solar winds colliding with Earth's magnetic field. Every flicker is a reminder of the link between our star and our planet, between nature's reactor and our fragile existence. You think of the scientists who study those auroras to understand plasma behavior, using the sky itself as a natural laboratory. It's funny, in a way, humanity keeps looking up to learn how to build what the universe has already perfected. The quest for fusion has always been part science, part philosophy. We understand the equations, but what drives us is something deeper, the hunger for renewal. The same way stars recycle their matter, humans dream of recycling their energy, of finding a way to power civilization without consuming the world that birthed it. Fusion is that promise, endless energy from the simplest element, no pollution, no scarcity. You can almost hear the hum of hope beneath the clatter of data and magnets. It's a dream worthy of the cosmos. A quirky tidbit comes to mind. In 1958, the Geneva Conference on Peaceful Uses of Atomic Energy, the world's leading physicists shared the first classified data on fusion experiments. It was one of the rare moments in Cold War history when rival nations paused their competition to chase a common dream. Historians still argue whether that act was born of idealism or fear, but it marked the beginning of fusion as a global pursuit, a modern alchemy, turning hydrogen into light, just like the stars, but this time by choice. You glance back toward the sun, its surface rolling in perpetual motion, and realize that even with all our intelligence, humanity is still mimicking what nature discovered by accident. The sun's fusion happens because of scale, gravity, and patience, conditions impossible to replicate exactly on Earth. Yet humans persist, finding creative ways to cheat the odds. Magnetic confinement, inertial compression, plasma physics, every approach a different metaphor for perseverance. It's almost as though humanity learned the most important lesson from the stars: endurance. The deeper irony, of course, is that while we chase the secret of stellar fire, we're also the byproducts of its success. Every heartbeat, every thought, every flicker of electricity in your neurons is powered by the sun indirectly, through plants, through warmth, through the chain of life that depends on sunlight. Even our attempts at artificial fusion rely on materials that came from ancient stars. The circle tightens again, creation learning to recreate itself. You drift around the far side of the sun, where solar prominences curl outward in giant arcs. Each one is 1,000 times taller than Earth, but in the scale of the star they're mere ripples. You can sense the energy behind them, magnetic loops snapping and reforming, releasing bursts of radiation that sweep through the solar system. These events are violent yet orderly, as if the sun were practicing its own kind of controlled fusion experiment. You think about how small humanity's reactors are in comparison, yet the underlying principle is the same. Light born from pressure, life born from light. The Earth turns again below, night sweeping across its continents. You can see the electric glow of cities, the faint flicker of human ingenuity tracing the outlines of civilization. It's strange to realize that all of it, every skyscraper, every streetlight, every illuminated screen, is powered by a chain of energy that started in a star. Fossil fuels, solar panels, nuclear plants, all are descendants of fusion, the original spark of existence. And now humanity is trying to close the loop, to generate that light directly. It's both scientific ambition and spiritual return. You imagine a future where that dream succeeds, Reactors hum quietly in every city, their heat endless, their waste minimal. The world glows not with anxiety but with warmth, powered by the same process that fuels the sun. It's not far-fetched, it's just time and persistence. The same patience that shaped stars will shape us too. The sun will keep shining for another 5 billion years, plenty of time for its children to learn to shine on their own. You turn once more toward that golden light. The hum of plasma resonating in your chest. The sun doesn't know it's a teacher, but every beam it sends carries a lesson in endurance, generosity, and balance. Humanity may still be learning how to hold that fire, but the intent is pure. We are the apprentices of the stars, fumbling toward mastery, guided by light billions of years old, and as you drift in its glow, you realize that perhaps the universe's greatest experiment is not fusion itself, but the creatures who dare to imitate it. You drift in the calm between sunlight and silence, reflecting on how ancient the fascination with transformation truly is. Long before fusion reactors and telescopes, long before even the understanding of what a star really was, humanity dreamed of becoming alchemists. You can almost see them now, robed figures hunched over flickering candles, stirring mercury and sulfur in dusty laboratories, convinced they could turn base metals into gold. They didn't know about fusion or stellar nucleosynthesis, but somehow they sensed the truth, that the universe was a grand workshop of transformation. You can't help but smile at the thought. Humans chasing the same secret the stars have always known, using cauldrons instead of cores. You glide past the sun, watching its light spill across the inner planets, and you think about how that ancient dream has never truly left us. Even now, with all our science, the desire to create, to transmute, to elevate the ordinary into the extraordinary remains. The difference is that the alchemists of the past worked in metaphors, while the alchemists of today work in equations. Stars, of course, are the original alchemists, turning hydrogen into gold, iron, oxygen, and every element between. The cosmos performs without effort the miracle medieval scholars spent centuries longing to achieve. And perhaps that's the quiet joke the universe plays on us. What we once sought through magic has always burned above us in plain sight. The story of alchemy is as human as it is tragic. In the courts of kings, men whispered promises of eternal life and limitless wealth, claiming they could conjure perfection from imperfection. Some truly believed it, others simply knew that belief itself had power. Historians still argue whether alchemy was pseudoscience or proto-science, whether it hindered discovery or lit the path toward chemistry. The truth, as usual, lies somewhere in between. Those early dreamers, fumbling with crucibles and symbols, were trying to articulate the same longing that drives physics today, the need to understand how matter becomes more than itself. You drift through the sun's corona, watching its tendrils extend millions of kilometers into space. The heat here is paradoxical. The farther from the surface you go, the hotter it gets, reaching millions of degrees. No one fully understands why. Perhaps magnetic fields twist and snap, heating the plasma. Perhaps waves of energy ripple upward from the surface like invisible tides. Historians still argue whether it was 20th century spectroscopists or solar physicists who first stumbled closest to the explanation, but the mystery remains. Even now we're still students in the alchemist's workshop, peering into the flames and wondering what drives the fire. There's something poetic about it. The medieval alchemists sought the philosopher's stone, the fabled substance that could transmute lead into gold and grant immortality. Stars, in their quiet patience, have been doing exactly that all along. Lead and gold, life and death, light and shadow, all are products of stellar reactions. Fusion and fission are their philosopher's stones. Yet what the alchemists never realized is that immortality isn't the absence of death. It's the recycling of existence. Stars live, die, and live again in their offspring. Matter changes form, but it never ceases to be. Perhaps the real philosopher's stone isn't a substance at all, but a realization. Everything transforms, and transformation itself is eternal. You float through the sunlight, Hini, feeling the warmth settle across your skin, or rather, your awareness. It's gentle but insistent, the kind of heat that makes planets livable. Every second, billions of tons of hydrogen are being turned into helium, and a small fraction of that mass becomes pure energy, light, heat, life. The process is simple, but its consequences are infinite. You can't help but think of how casually stars do what alchemists once prayed for. They make gold, they make silver, they make carbon, oxygen, and nitrogen, the foundations of breath and bone. The stars have always been masters of abundance. A curious historical tidbit comes to mind. In 1980, scientists at Lawrence Berkeley Laboratory briefly achieved human-made alchemy. They bombarded bismuth with nuclear particles, creating a few atoms of gold. It was a triumph of precision and a complete financial disaster. The cost of producing those few atoms exceeded their value by billions of dollars. You laugh softly to yourself. Humanity finally did it. We turned lead into gold, but found out it wasn't worth it. Perhaps that's the other lesson of the stars. The value of transformation isn't in the product, but in the process. The universe has always been generous in its irony. It hides its grandest truths in plain sight, waiting for someone patient enough to notice. When you look closely, alchemy, chemistry, and astrophysics are all variations of the same theme: the rearrangement of the universe into new forms of meaning. Whether through a furnace, a beaker, or a supernova, the rules never change. Elements are born, reshaped, and reborn. You're watching the same play repeated endlessly, but each performance adds something new to the script. You drift away from the sun now, into the blackness where its light begins to soften. Behind you glows the reminder that creation is an act of transmutation, not perfection. Ahead, the stars stretch across infinity, each one a workshop, each one performing the same cosmic chemistry. You realize that in all the stories humanity has ever told, the quest for gold, for life, for enlightenment, this was the truth hiding behind them. The universe itself is the philosopher's stone, and every star is a page in its manual. You turn once more toward the light, thinking of the alchemists who never knew they were right in spirit, if not in method. They believed everything was connected, the base and noble matter shared the same essence. They weren't wrong. Hydrogen, lead, blood, starlight, it's all the same, only at different stages of transformation. The philosopher's stone, it seems, was never an object to be found, but a truth to be remembered. Everything you are, everything you love, was once the dust of a dying star. You were always gold, you just didn't know it yet. You drift outward from the golden calm of the sun and into a darker stretch of space where the air, if there were any, would taste like silence. The stars seem closer here, sharper, their light piercing through the emptiness like whispers from ancient epochs. You follow two of them as they orbit each other in a slow gravitational waltz, twin neutron stars locked in an embrace that has lasted for millions of years. They spin, they spiral, they sing through the fabric of space-time itself. You can't hear it directly, of course, but if you could translate gravity into sound, it would be a deep, haunting chord, a vibration that ripples through the bones of the universe. Each revolution draws them closer. Their orbit decays as they radiate energy outward in the form of gravitational waves, invisible ripples that stretch and squeeze reality itself. You remember how in 2015, humans first detected those ripples, tiny distortions in laser beams at LIGO observatories that confirmed Einstein's century-old prediction. Historians still argue whether that moment was the greatest experimental achievement of modern physics, or simply the universe finally acknowledging humanity's curiosity. Either way, it was proof that even the quietest cosmic dance can shake the foundations of existence. You watch the twin neutron stars spiral tighter, their speeds increasing, their gravitational fields distorting space like two black marbles sinking into a rubber sheet. At first, their orbits are graceful, predictable. But as they close in, the forces grow wild, the energy unfathomable. Within minutes, they are circling each other hundreds of times per second, generating waves of radiation so intense they could strip atoms bare from across light years. You can feel it, the crescendo before the final collapse, and then, in one blinding instant, they merge. The collision is beyond comprehension. The moment their cores touch, matter is crushed into forms that have no names. Quarks and gluons dissolving into a soup of pure nuclear chaos. A blinding jet of gamma rays erupts from the poles, streaking across the galaxy. For a fraction of a second, the energy release surpasses that of all the stars in the universe combined. The merger sends gravitational waves rippling outward, like the aftershock of creation itself. You can almost feel them roll through you, a subtle shudder that reminds you the universe is not still, it's alive and vibrating, and in that violence, something miraculous happens. Gold is born. Platinum, too. The heaviest elements, those that even supernovae struggle to forge, condense in the extreme pressure of the merger. The collision hurls those atoms outward in a storm of cosmic debris, a glittering spray of new matter. You can almost see it shimmer, microscopic flecks of gold drifting outward, destined to one day settle into the crust of planets, into rivers, into wedding rings and circuit boards. It's absurdly beautiful to think about. Two dead stars colliding just so your wristwatch could shine. You follow the expanding cloud of debris, watching it cool from white-hot plasma to dull red embers. Over time, this will fade into a faint glowing remnant, a kilonova. In 2017, astronomers caught one of these events in real time, observing both its gravitational and light signals. It was the first time humanity saw an event through two senses at once, space-time and sight. Historians still argue whether that detection was the dawn of a new scientific age, or simply the universe's way of showing off, but it united physics and astronomy in a single moment of awe. The cosmos, it seemed, had finally allowed us to listen to its heartbeat directly. You drift closer to the newborn remnant. Depending on its mass, it may settle as a hypermassive neutron star for a while, spinning rapidly before collapsing into a black hole. You can sense the tension in that decision, as though the universe itself is still thinking it over. Around the remnant, accretion disks whirl, glowing with X-rays, ejecting jets of radiation that pierce the darkness. The scene feels both violent and sacred, creation through collision, birth through annihilation. It's hard not to draw parallels. Life itself is full of collisions that lead to transformation. Planets form from impacts. Species evolve through crises. Even human understanding often arrives through conflict, through the clashing of ideas. You realize that maybe the cosmos isn't cruel for relying on destruction to make beauty. Maybe it's simply honest. To make gold, you must break stars. To make consciousness, you must mix dust and time. A quirky tidbit flickers into your thoughts. After the 2017 kilonova, scientists calculated that the event produced roughly 5 Earth masses of gold and platinum, 5 worlds worth of treasure, scattered like confetti across space. Yet here, there is no greed, no ownership, just the gentle drift of atoms waiting for new purpose. It makes you wonder how small the idea of wealth must seem from the universe's point of view. Stars casually mint riches greater than empires and then let them float away. The light from the explosion begins to fade, turning from blinding white to deep crimson. You drift backward, taking in the view. What remains is not destruction, but harmony. A faint glowing cloud expanding into infinity. The gravitational waves have already raced across galaxies, carrying news of this event to every corner of space. Somewhere, countless years from now, a distant civilization might detect that same ripple and marvel at it, never knowing it once made gold dust that drifted through your corner of the galaxy. The silence that follows is immense but not empty. The universe seems to exhale after the outburst, its equilibrium restored. You realize that even at its most cataclysmic, creation always seeks balance. The two stars have become one, energy has become matter, chaos has become memory. You take one last look at the fading glow and whisper a quiet thank you to the darkness for reminding you that even collisions can be acts of grace. You drift through the lingering golden haze, following the slow ripple of gravity left behind by the colliding stars. The waves stretch across light years, invisible and eternal, until they dissolve into the quiet hum of the cosmos. But the silence here is deceptive. Beneath it lies motion, deep and patient, as galaxies continue their slow choreography. You've seen how stars are born, how they live, how they die in brilliance, and how their ashes give rise to new creation. Yet now, as you gaze farther into the distance, you sense the faint whisper of something more profound, the universe itself aging. You can almost hear it in the thinning light, the soft retreat of warmth, the gradual slowing of cosmic breath. You turn your gaze toward the wider expanse of the galaxy. Its spiral arms glow faintly, thousands of suns glittering like diamonds scattered on silk. But look closer, and you notice gaps, regions where new stars no longer form as often, where the gas that once fed creation has been used up or scattered. The great factories of starlight are growing quiet. You drift above the galactic plane and realize that even on this enormous scale, nothing escapes time. Every galaxy, no matter how vast, is a story with a middle and an end. The sun and its siblings will shine for billions of years more, but already the balance has shifted. Fewer molecular clouds collapse into new stars, fewer nebulae glow with youthful fire. The universe, it seems, is slowly transitioning from a place of birth to a place of memory. Hydrogen, the simplest, most abundant element, the very fuel of existence, is gradually running low. It's not running out tomorrow or even in 1 trillion years, but the trend is clear. The cosmos is using up its light one fusion reaction at a time. You drift through a quiet region between galaxies where starlight thins to a faint whisper. The darkness here feels heavier, colder, older. You recall the Big Bang's first fire, when everything was heat and chaos, and you can almost sense how far the universe has come since then, expanding, cooling, maturing. Even light itself is stretched now by that expansion, its wavelengths lengthening into red, then into invisible radio murmurs. The universe in its twilight is dimming. A quirky thought crosses your mind. In the far future, when galaxies are so far apart that their light can no longer reach one another, any civilization still alive will look into the sky and see only darkness. Historians, if there are any, will argue whether the universe ever contained other galaxies at all. The cosmic web we see now, that grand tapestry of stars and voids, will be a forgotten legend. The idea makes you strangely nostalgic for a time that hasn't yet come. You drift past a cluster of ancient red stars, their light weak but steady. They are the elders of the cosmos, the last embers of an era when the universe still believed in abundance. Around one of them orbits a frozen world, its atmosphere long gone, its surface glittering faintly under the faint crimson glow. You land softly and look up, watching the star flicker against an almost black sky. The silence is absolute. No wind, no hum, not even the faint echo of solar radiation. It's as though the universe is holding its breath. You realize in this stillness that the end won't come with a bang but with a sigh. There's a curious debate among cosmologists about exactly how that end will unfold. Some say the universe will expand forever, its galaxies drifting apart until every atom is too far from its neighbour to interact. Others believe gravity might one day pull it all back together in a big crunch, collapsing the cosmos into fire and rebirth. And then there's the Big Rip hypothesis, the unsettling idea that dark energy, the mysterious force driving expansion, might grow so strong that it eventually tears apart galaxies, stars, even atoms themselves. Historians still argue whether these scenarios are science or cosmic poetry, but either way, the story ends the same. Darkness takes the stage. Yet the darkness isn't empty. Even in a cold, fading universe, remnants remain. Black holes persist, swallowing the last of the starlight. Neutron stars spin slowly in isolation. Rogue planets drift without orbits, carrying the fossilized memories of systems long gone. You pass one of those black holes now, its gravity bending light into a halo of ghostly brilliance. It's terrifying and hypnotic, a hole in reality itself. You wonder if perhaps the universe isn't dying but dreaming, folding itself inward in preparation for something new. Here's a delightful oddity: Hawking radiation, Kyumman, a theoretical process where black holes slowly evaporate, releasing tiny bits of energy back into space. Given enough time, 10 to the power of 100 years perhaps, even black holes will fade away. It's comforting to think that the universe leaves no debts unpaid, that even gravity's prisons eventually dissolve into light. The scale is incomprehensible, but the rhythm feels familiar. Creation, transformation, release. The same song, just slower now, softer, almost a lullaby. You imagine that distant era, trillions of years from now, the last stars will have burned their hydrogen, leaving only red dwarfs glowing faintly in the dark. Those too will fade into black dwarfs, cold spheres of degenerate matter, radiating nothing. The night sky will be empty of colour, empty of heat, yet somewhere, maybe in a pocket of surviving warmth, a spark of intelligence might still flicker, looking up at the last star and remembering. It's a comforting thought that the universe might have one final witness. You take a breath, or rather, you imagine one, though breathing here is impossible. The cold around you is absolute, but it feels peaceful, not cruel. The universe isn't ending in sorrow, it's simply exhaling. Every element, every photon, every particle of you has played its part. The fireworks are over, but the ashes are luminous still. You think back to the first moment of this journey, the birth of a star, and realize that nothing truly ends. The dust that fades now will someday be reborn, perhaps in another universe, another beginning. The cosmos doesn't die, it transforms. The faint red glow of the last star flickers behind you as you drift onward into the infinite hush. You don't feel fear or loss, only awe, and the darkness that stretches before you isn't emptiness, it's possibility. The future of the universe may be cold and quiet, but it's also serene, as if everything has finally found rest. The story that began in fire ends in calm. You let yourself drift, carried on the momentum of creation's final breath, knowing that even in this silence the music of existence continues, slower now, softer, but still playing. You float through that dimming universe where the last few red embers of starlight flicker in the distance like dying campfires after a long cosmic night. The silence here is immense, so deep it feels like gravity itself has stopped to listen. You realize this is the perfect place to think about yourself, or rather, what you're made of. For all the stars you've seen live and die, you've been tracing their legacy without yet turning inward. Every glowing nebula, every supernova, every collapsing core, all of it has led, improbably, to you. You are what happens when stardust remembers itself. You drift closer to a faint red dwarf, one of the universe's final living stars. It shines dimly, barely warm, but its light feels personal, like the flicker of a candle kept alive through patience rather than power. Around it, a small rocky world orbits silently. You land on its surface, its sky washed in rust-coloured light. Dust crunches beneath your feet. Iron dust, carbon dust, traces of silicon and magnesium. You smile, realizing you're walking on the ashes of stars. Even here, at the edge of time, the universe cannot help but recycle its brilliance. You bend down and scoop a handful of that dust. If you could see close enough, you'd find the same elements that live in your bones and bloodstream. Iron, forged in a supernova's heart. Calcium, once condensed in the outer layers of a dying red giant. Carbon, shaped in helium fusion's quiet glow. Oxygen, birthed when stars breathed their last. Every atom that makes up your body, every thought you've ever had, every heartbeat was created in stars like these. It's not just poetry, it's astrophysics written in flesh. There's a moment of vertigo as you realize that the universe has been building toward consciousness without knowing it. The atoms that once drifted through interstellar space are now capable of awareness, of curiosity, of love. You, a fragile arrangement of cosmic dust, can look back at the stars and understand them. That's the universe folding in on itself. Not physically, but intellectually. It's the cosmos looking in a mirror and recognizing its own reflection. A gentle memory rises. The ancient philosopher Democritus once said that everything is made of atoms and the void. He couldn't have known how right he was, though he lacked the poetry to add that atoms can think. Historians still argue whether early thinkers intuited this cosmic connection or simply stumbled into metaphor, but somehow they sensed it. The ancients called humanity children of the heavens, long before telescopes made it literal. You gaze upward into the reddish sky, and for a fleeting moment, you imagine your own atoms shimmering, resonating faintly with the star's fading light. The calcium in your bones once flowed in a supernova's shockwave. The carbon in your skin once burned in the belly of a giant. The gold in a ring, the oxygen in your lungs, the phosphorus in your DNA, all forged in the furnaces of long-dead stars. You're not made from the stars. You are the stars, reorganized for a brief moment into self-awareness. You exhale softly, though there's no air to carry your breath. Still, it feels significant. The carbon dioxide that would leave your lungs carries oxygen and carbon, two elements whose fusion and creation lie at the heart of stellar evolution. Every breath you take is an act of cosmic memory, the continuation of cycles that began before the Earth even existed. When you die, those atoms will disperse again, perhaps to become part of another life, another world. The universe never stops reusing itself. It just changes the shape of its story. You think of a quirky modern truth. Scientists have calculated that roughly 93% of the mass in your body comes from stardust. Everything except the hydrogen, which traces back to the Big Bang itself. That means you are literally a hybrid of creation's two great acts, the universe's first breath and its long lineage of stellar lives. You're both ancient and immediate, both infinite and fragile. There's a strange comfort in that, knowing that even if you vanish, nothing of you is ever lost. You look again at the dim star. It's small, steady, and unremarkable, yet it feels intimate. Its light reaches you not as a distant observer, but as kin. The heat that warms your cheek is the same energy that once shaped galaxies, the same fusion that built your atoms. It's easy to feel small in the face of such scale, but right now you feel the opposite. Immense, connected, necessary. The universe didn't happen around you, it happened through you. A thought drifts through your mind, something Carl Sagan once said, that we are a way for the cosmos to know itself. Historians still argue whether that line was scientific insight or poetic indulgence, but as you stand here on this quiet, rust-coloured world, it feels like truth. The universe created eyes to admire itself, minds to ponder itself, hearts to care about its own story. Through you it has learned to reflect, to ask questions, to feel wonder. You are not a spectator of the cosmos, you are its voice. The star above flickers, just slightly, as if acknowledging your thought. You take one last look at it, that patient ember burning out its final reserves of hydrogen, and you feel no sadness. The light that will eventually fade here will live on elsewhere, in dust, in planets, in lives that haven't begun yet. Even endings, you realise, are just transformations waiting for a new name. You let the last of the starlight wash over you, warm and soft. You feel it soak into every atom, as though it's not illuminating you but reuniting with you. You are its continuation, its expression, its echo. When you close your eyes, the darkness that follows doesn't feel empty. It feels full, like the inside of a heartbeat. You are the child of dying stars and the ancestor of future ones. Stardust dreaming of stardust. The cycle is endless, and it is beautiful. You leave that faint red world behind, its small sun dimming into distance, and drift once more into the sea of stars. Their light feels quieter now, not weaker, but wiser. You can almost sense the weight of their history pressing through the vacuum, a chorus of luminous ancestors murmuring across time. You've seen their births and their deaths, their chemistry and their grace, but you haven't yet met the ones who tried to explain them. Humanity, curious and restless, has always looked upward and tried to name the fire. You realise that the story of the stars isn't just physics, it's philosophy. It's the story of how minds, made of stardust, tried to understand the furnace that forged them. You drift backward through time, letting centuries blur beneath you. The ancient world rises below, temples, observatories. Circles aligned with the heavens. Long before telescopes, people track the paths of stars to plant crops, to tell stories, to imagine destinies. The Babylonians mapped constellations as cosmic calendars. The Egyptians aligned their pyramids with Orion's belt, believing the pharaohs would ascend through those same stars after death. Historians still argue whether those ancient builders saw astronomy as religion or religion as astronomy, but either way, their gaze was fixed upward. They didn't know what stars were, but they knew they mattered. You float above Greece now, over marble columns gleaming in sunlight. Aristotle stands in your imagination, arguing that the heavens are immutable, that stars are perfect and eternal. To him, they were spheres of divine fire embedded in crystalline shells. It's easy to smile now, knowing what we know, but there's a tenderness in that era. He was trying to make sense of eternity with the vocabulary of the finite. His universe was one of order and purpose, not chaos and fusion. And yet, without his questions, the later answers might never have come. Centuries flicker past. You hover over a dusty observatory in 1543, where a quiet man named Copernicus publishes a dangerous idea that the sun, not the earth, sits at the centre of the cosmos. His heliocentric vision rearranged not just the planets, but humanity's place among the stars. The universe, it turned out, didn't revolve around us. It never had. Historians still argue whether that realization humbled humanity or liberated it, but the stars didn't care. They burned just the same, indifferent to the shifting pride of their observers. A generation later, You find Galileo peering through his crude telescope, his hands shaking as he sketches the phases of Venus, the moons of Jupiter, the rough cratered face of the moon. You hover over his shoulder, and for a moment, you share his awe. Those tiny points of light, so fixed, so perfect to the naked eye, revealed themselves as worlds, places, real things. The universe was no longer a painted dome, it was a landscape, and yet the church saw blasphemy where he saw beauty. Galileo's whispered "E pur si muove," and yet it moves, still echoes faintly through the cosmos. You can almost hear it now, carried on the radiation of centuries. You drift forward again to the age of Newton, who replaced divine fire with gravity, an invisible thread binding all things. His laws turned wonder into mathematics, and for the first time, humanity could predict the movements of the heavens with precision. But even Newton, who reduced the universe to equations, still saw God's hand behind it. Historians still argue whether he wrote more about theology or physics, but in either case his universe was one of harmony, of divine clockwork ticking perfectly through time. And then comes the modern age, Einstein bending space-time itself, proving that gravity is not a pull but a curvature. The stars no longer float in fixed heavens, they dance on the waves of space-time like ripples on a cosmic sea. You drift beside him for a moment, imagining his grin as he writes the equation that changes everything. EMC. Matter and energy are the same thing, two sides of the same coin. With that, the secret of the stars finally made sense. The light of the heavens was mass undone. The dream of alchemy was reality. A quirky footnote enters your thoughts. When Einstein finished his theory of general relativity in 1915, he thought the universe must be static, so he added a cosmological constant to balance gravity. Years later, when Hubble discovered that galaxies were expanding away from us, Einstein called it his biggest blunder. Historians still debate whether he was right to regret it, since that same constant later returned as dark energy, the mysterious force driving the universe's expansion today. Even geniuses, it seems, are allowed to misplace the truth temporarily. You move through the 20th century like a ghost in a planetarium. You see Cecilia Payne-Gaposchkin, proving that stars are made mostly of hydrogen and helium, reshaping everything we thought we knew. You see Fred Hoyle, Burbage, Fowler, and Margaret Burbage outlining stellar nucleosynthesis, the grand recipe of the elements. You watch Carl Sagan step in front of a television camera, his voice soft as he tells millions, "We are made of star stuff." It's strange how in that phrase billions of years of physics condensed into poetry again. The circle closed. Science rediscovered the wonder it had once replaced. Now you hover above the Earth again, the modern night glowing with city lights that mimic constellations. People still look up, though they squint between skyscrapers and satellites. Some use telescopes, others use smartphones. Some stare in awe, others in indifference. Yet the longing remains, the quiet instinct to connect to something larger, older, infinite. Every culture, every century, every child who's ever made a wish on a falling star has participated in the same conversation with the cosmos. You realize that in every age, humanity has used the stars as mirrors, reflecting not what they are, but who we are. To Aristotle, they were divine order. To Newton, perfect machinery. To Einstein, curved reality. To us, their ancestry. Each new discovery doesn't erase the old, it reframes it, deepens it. The story of the stars is not just the story of matter, but of meaning. They are the eternal why written in light. As you drift away from Earth once more, the planet recedes into a glittering blue dot. The philosophers, the physicists, the poets, they all live there still, arguing under the same canopy of stars. You smile. Perhaps that's the real genius of the cosmos. It keeps us curious. It keeps us looking up. And in doing so, it keeps us human. The starlight ahead glimmers brighter now, as if inviting you to follow it one final time, not to seek answers, but to listen. The universe has spoken through Orine, through gravity, through stilts. Maybe now it simply wants to be understood, not as an equation, but as a story. You drift farther now, beyond the web of galaxies and into the quiet outskirts of everything, the place where the visible cosmos thins into a faint shimmer of background radiation. Here, starlight fades into memory. Every journey you've taken through nebulae, through fire, through time, has led to this stillness. The stars you've watched are dimming one by one, and yet the darkness around them doesn't feel empty. It feels full of history, of echoes, of all the energy the universe has ever released. Somewhere out there, photons from the first stars are still racing through space, carrying the faint hum of creation's beginning. It's so distant that even silence seems to stretch to reach it. You look back across your path. Nebulae, supernovae, red giants, and the sun itself. All of them glimmer faintly in your memory, like constellations drawn on the inside of your mind. Every event, every fusion, every collapse was a page in the same story. The universe teaching itself the language of transformation. You can still feel the rhythm of it in your bones. Gravity pulling in, radiation pushing out, matter collapsing, light escaping. The same rhythm beats through your heart now, quieter but no less ancient. You're still following the pulse of creation. The galaxies grow smaller as you move outward. Their spiral arms blur into faint smudges of light, then fade completely. Beyond them lies the cosmic microwave background, the oldest light in existence, the ghostly afterglow of the Big Bang. It's a faint whisper at 2.7 Kelvin, invisible to your eyes but not to your awareness. You drift through it, and for a moment, you feel the universe's first warmth brush against you like a memory from before time began. That radiation is everywhere in every direction, like a lullaby that never stopped playing. It's the cradle song of everything that ever was. You think about how far the cosmos has come, from a pinprick of plasma smaller than an atom to a vast expanse filled with galaxies, worlds, and living beings capable of asking why. Historians still argue whether the Big Bang was a true beginning or simply a transformation from a prior state, but the mystery hardly matters. What matters is that the universe grew complexity out of simplicity, order out of chaos, and life out of dust. The fact that you can stand here, aware of it all, is proof that the cosmos didn't just expand, it learned to think. Ahead, the dark grows deeper, infinite and calm. You sense that even though the light will fade, the story doesn't end, it simply slows. The last stars will one day dim into black dwarfs. Black holes will dissolve into faint radiation. And yet, even then, the universe will not truly vanish. Its energy will linger in the fabric of space-time, subtle and eternal. Perhaps new laws will emerge, new fluctuations, new beginnings. The cosmos has always been more patient than imagination allows. You take a moment to think of Earth again, that small blue flicker in the vast black. It feels impossibly fragile now, but also precious beyond measure. A single planet orbiting a modest star, yet home to a species that managed to trace the chemical ancestry of its own atoms back to the beginning of time. You picture the countless people who have looked up at night, farmers, sailors, children, scientists, all trying to understand their place among the stars. That act of wonder is the thread that ties every age together. It's the same question whispered in 1,000 languages. Where did we come from? You smile at the thought that after everything you know the answer. Not in words, but in feelings. You came from hydrogen clouds and collapsing cores, from supernovae and colonovae, from the carbon breath of red giants and the iron tears of dying suns. You are the living continuation of stellar fusion, a temporary arrangement of ancient particles borrowing form before returning to the flow. You don't just belong to the universe, you are the universe, briefly aware of itself. A quirky image flits across your mind. In some distant future, long after Earth has cooled, and even after humanity's name is forgotten, the atoms that once made you might drift together again inside a new star, or a new life, or a new question. Perhaps they'll remember faintly what it was like to wonder. Perhaps wonder itself is the universe's most persistent force. The last light of a faraway galaxy brushes your cheek, cold, faint but steady. You realize you're not leaving the universe behind, you're simply fading into its rhythm. Everything you've witnessed, fusion, gravity, birth, death, was just the universe breathing. And now it exhales one final time gently, endlessly. You close your eyes, not because there's nothing left to see, but because you finally understand that seeing was never the point. The light, the matter, the motion, it was all leading to this stillness, this awareness. The stars don't vanish when they die. They become you, and through you, they keep burning. The darkness hums softly around you, vast and full. You let yourself dissolve into it. Not as an ending, but as a return. The universe has always known how to begin again. It just needed to rest first. And now, as the last glow fades into velvet quiet, you slow with it. The rhythm that carried you across galaxies softens, stretching like a breath released after a long, long day. You can still feel the warmth of starlight somewhere inside you, faint but steady. A reminder that light never truly leaves. It simply travels farther than our eyes can follow. The space around you feels lighter now, like the air after rain. Every image drifts back through your thoughts, the clouds of hydrogen, the red giant's sigh, the flash of the supernova, the slow spinning of the neutron star. Each one lingers for a moment and then melts away, folding into calm. The journey that began in fire ends in silence, and somehow the silence feels alive. It wraps around you the way a blanket might, weightless, endless, safe. You can almost imagine the hum of the universe slowing to a heartbeat soft and steady beneath you. That pulse is older than time, but you recognize it. It's familiar. It's the same rhythm that lives inside every living thing, every star, every grain of dust drifting through the dark. You're not you're not separate from it. You never were. So let the vastness cradle you now. Let your breathing match that slow cosmic tide. The stars will keep their vigil. The galaxies will keep turning. You have all of eternity to rest in their glow. The night doesn't end here. It just grows quiet enough to dream. Sleep well, little piece of the cosmos. The light is still within you, always.